Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Network Devices, Part 1. Today we're going to be talking about Layer 1 devices, Layer 2 devices, and then we're going to conclude with Layer 3 devices. There's a fair amount of information to cover, so let's go ahead and dive into this session. Of course, I'm going to begin with Layer 1 devices. Well, before I start talking about the Layer 1 devices, we need to talk about the Open System Interconnection model, the OSI model. It was developed as a way to help disparate computing systems to communicate with each other. The OSI reference model has 7 layers. Layer 1 is the physical layer, Layer 2 is data link, Layer 3 is network, Layer 4 is transport, Layer 5 is session, Layer 6 is presentation, and Layer 7 is application. We're going to be discussing the bottom 3 layers, Layers 1, 2, and 3 today. Now, most devices do function at more than one layer of the OSI reference model. But when it comes time to determining where they fit into the model, you must first determine the highest level at which they operate, because that's where they fit into the OSI model. To do that, you must know what they do and how that relates to the OSI model. And with that, let's talk about analog modems. The word modem is actually derived from a contraction of modulator, demodulator. Modems were developed to take a digital signal coming from a digital node and convert it to an analog signal, modulating the signal, and placing it on a wire. In return, it would accept an analog signal from the wire and convert it, demodulating the signal, back to a digital signal that the node can understand. Modems were developed to create a connection between network segments via the public switched telephone network using the plain old telephone system. Now, modems provide for a single connection to a network, and they're only concerned about the wire. And the wire resides on the physical layer, Layer 1 of the OSI model. It doesn't care where the signal comes from, it just does its job. Then there's the hub. A hub functions as a concentrator or repeater in that it doesn't care where the signal comes from or where the signal is going. Kind of like the modem. It takes an electrical signal that arrives on a port and replicates that signal out all of its other ports. A hub may have just a few ports or it may have many ports. And for a variety of reasons, the hub is not very common anymore in the modern network. So now let's move on to Layer 2 devices. The first Layer 2 device that we're going to talk about is the switch. A switch utilizes an application-specific integrated circuit chip, an ASIC chip. The ASIC chip has specific programming that allows the switch to learn when a device is on the network and which ports it is connected to via that device's Layer 2 MAC address. That's what makes a switch a Layer 2 device. A switch may have just a few ports or it may have many ports, kind of like the hub. And although a switch is smarter than a hub, it can still be very simple or it can be highly complex and programmable. A switch can only communicate with local network devices. Another Layer 2 device that we need to talk about are wireless access points, the WAP. A WAP is a specific type of network bridge that connects or bridges wireless network segments with wired network segments. The most common type of WAP bridges an 802.11 wireless network segment with an 802.3 Ethernet network segment. Just like a switch, a wireless access point will only communicate with local network devices. Now let's move on to Layer 3 devices. And first up is the multi-layer switch. A multi-layer switch provides normal Layer 2 network switching services but it will also provide layer 3 or higher OSI model services. The most common multi-layer switch is a layer 3 switch. It not only utilizes an ASIC chip for switching, but that ASIC chip is also programmed to handle routing functions. This allows the device to communicate and pass data to non-local network devices. A multi-layer switch is a highly programmable and complex network device. A multi-layer switch may have just a few ports, or it may have a lot of ports. They're not very common in the small office, home office network because they're really expensive. You're more likely to find them in an enterprise local area network. Now let's move on to the router. A router is the most common network device for connecting different networks together utilizing the OSI model's layer 3 logical network information. That's what makes a router a layer 3 device. The router uses software programming for decision making as compared to the switch's use of an ASIC chip. The router uses this programming to keep track of different networks and what it considers to be the best possible route to reach those networks. A router can communicate with both local and non-local network devices. In most cases, a router will have fewer ports than a switch. Now that concludes this session on the Introduction to Network Devices Part 1. We talked about Layer 1 devices, we talked about Layer 2 devices, and we concluded with a couple of Layer 3 devices. Now on behalf of PACE IT, thank you for watching this session, and I'm pretty certain I'll do another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Network Devices Part 2. Today we're going to discuss some security network devices, and then we'll move on to some optimization and performance devices. And with that, let's go ahead and begin this session. And we will begin by talking about security devices. First up is the firewall. Now, a firewall can be placed on routers or hosts in that it can be software-based, or it can be its own device. A firewall functions at multiple layers of the OSI model, specifically at layers 2, 3, 4, and 7. A firewall can block packets from entering or leaving the network, and it does this through one of two methods. It can do it through stateless inspection, in which the firewall will examine every packet that enters or leaves the networks against a set of rules. Once the packet matches a rule, the rule is enforced and the specified action is taken. Or it may use stateful inspection. This is when a firewall will only examine the state of a connection between networks. Specifically, when a connection is made from an internal network to an external network, the firewall will not examine any packets returning from the external connection. It only cares about the state of the connection. As a general rule, external connections are not allowed to be initiated with the internal network. Now, firewalls are the first line of defense in protecting the internal network from outside threats. You can consider the firewall to be the police force of the network. Then there is the Intrusion Detection System, the IDS. An IDS is a passive system designed to identify when a network breach or attack against the network is occurring. They're usually designed to inform a network administrator when a breach or attack has occurred, and it does this through log files, text messages, and or through email notifications. An IDS cannot prevent or stop a breach or attack on its own. The IDS receives a copy of all traffic and evaluates it against a set of standards. The standards that it used may be signature-based. This is when it evaluates network traffic for known malware or attack signatures. Or the standard may be anomaly-based. This is where it evaluates network traffic for suspicious changes. Or it may be policy-based. This is where it evaluates network traffic against a specific declared security policy. An IDS may be deployed at the host level. When it's deployed at the host level, it's called a host-based intrusion detection system, or HIDS. More potent than the intrusion detection system is the intrusion prevention system, the IPS. An IPS is an active system designed to stop a breach or attack from succeeding in damaging the network. They're usually designed to perform an action or set of actions to stop the malicious activity. They will also inform a network administrator through the use of log files, SMS, text messaging, and or through email notification. For an IPS to work, all traffic on the network segment needs to flow through the IPS as it enters and leaves the network segment. Like the IDS, all of the traffic is evaluated against a set of standards, and they're the same standards that are used on the IDS. The best placement on the network segment is between a router, with a firewall hopefully, and the destination network segment. That way all the traffic flows through the IPS. IPSs are programmed to make an active response to the situation. They can block the offending IP address, they can close down vulnerable interfaces, they can terminate network sessions, they can redirect the attack, plus there are more actions that an IPS can take. The main thing is that they are designed to be active, to stop the breach or attack from succeeding in damaging your network. Let's move on to the Virtual Private Network Concentrator, the VPN concentrator. Now this will allow for many secure VPN connections to a network. The concentrator will provide proper tunneling and encryption depending upon the type of VPN connection that is allowed to the network. Most concentrators can function at multiple layers of the OSI model. Specifically, they can operate at layer 2, layer 3, and layer 7. Now, outside of internet transactions, which use an SSL VPN connection at layer 7, most concentrators will function at the network layer, or layer 3 of the OSI model, providing IPsec encryption through a secure tunnel. Now let's talk about optimization and performance devices. We will begin by talking about the load balancer. A load balancer may also be called a content switch or content filter. It's a network appliance that is used to load balance between multiple hosts that contain the same data. This spreads out the workload for greater efficiency. They're commonly used to distribute the requests or workload to a server farm among the various servers in the farm, helping to ensure that no single server gets overloaded with work requests. Then there's the proxy server. A proxy server is an appliance that requests resources on behalf of a client machine. It's often used to retrieve resources from outside untrusted networks on behalf of the requesting client. It hides and protects that requesting client from the outside untrusted network. It can also be utilized to filter allowed content back into the trusted network. It can also increase network performance by caching or saving commonly requested web pages. Now that concludes this session on the Introduction to Network Devices Part 2. We talked about some security devices that you may find on your network. And we concluded with optimization and performance devices that may also be present. Now, on behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications Part 1. Today I'm going to be discussing the basics of the virtual private network, and then I'm going to move on to protocols used by virtual private networks. Now there's a whole lot of stuff to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about the basics of the virtual private network. A virtual private network, or VPN, is used by remote hosts to access a private network through an encrypted tunnel through a public network. Once the VPN connection is made, the remote host is no longer considered remote. It's actually seen by the private network as being a local host. There are many advantages to that, but I'm not going to cover them right now. Even though the network traffic may pass through many different routes or systems, it's seen by both ends as being a direct connection. The use of the VPN can help to reduce networking costs for organizations and business. The cost reduction is partially achieved because the VPN doesn't require the use of a dedicated leased line to create that direct connection. There are several different types of VPNs. There is the site-to-site VPN, which allows a remote site's network to connect to the main site's network and be seen as a local network segment. VPN concentrators on both ends of the VPN will manage that connection. Then there's the remote access VPN, which is also called a host-to-site VPN. It allows select remote users to connect to the local network. A VPN concentrator on the local network will manage the connection coming in from the remote users. The remote system making the connection uses special software called VPN client software to make that connection. The third type of VPN is the host-to-host VPN, which is often called an SSL VPN. It allows a secure connection between two systems without the use of VPN client software. A VPN concentrator on the local network manages the connection. The host seeking to connect uses a web browser that supports the correct encryption technology, which is either SSL or more likely TLS, to make the connection to the VPN concentrator. It's time to discuss some protocols used by the virtual private network. The big protocol for VPNs is called Internet Protocol Security, IPsec, which isn't actually a protocol in itself, but a whole set of protocols. IPsec works at layer 3 of the OSI model or above. It's the most common suite of protocols used to secure a VPN connection. IPsec can be used with the Authentication Header Protocol, or the AH protocol. AH only offers authentication services but no encryption. So it authenticates the user, but there is no encryption of the session. Or IPsec can be used with Encapsulating Security Payload Protocol, or the ESP protocol. ESP both authenticates and encrypts the packets. It is the most popular method of securing a VPN connection. Both AH and ESP will operate in one of two modes. The first mode is transparent mode. That is between two devices, as in a host-to-host VPN. Or they can be used in tunnel mode, which is between two endpoints, as in a site-to-site VPN. IPsec implements Internet Security Association and Key Management, ISACAMP, by default. ISACAMP provides a method for transferring security key and authentication data between systems outside of the security key generating process. It is a much more secure process. Then we have Generic Routing Encapsulation, GRE. GRE is a tunneling protocol that is capable of encapsulating a wide variety of other network layer protocols. It's often used to create a subtunnel within an IPsec connection. Why is that? Well, IPsec will only transmit unicast packets. That's one-to-one communication. In many cases, there's a need to transmit multicast, which is one-to-some communication, or broadcast, which is one-to-many communication, packets across an IPsec connection. By using GRE, we can get that accomplished. Then there's point-to-point tunneling protocol, PPTP. This is an older VPN technology that supports dial-up VPN connections. On its own, it lacked native security features, so it wasn't very secure. But Microsoft's implementation included additional security by adding GRE to point-to-point tunneling protocol. Transport layer security is another common VPN protocol. TLS is a cryptographic protocol used to create a secure encrypted connection between two end devices or applications. It uses asymmetrical cryptography to authenticate endpoints and then negotiates a symmetrical security key, which is used to encrypt the session. TLS has largely replaced its cousin, Secure Socket Layer Protocol, and TLS works at layer 5 and above of the OSI model. Its most common usage is in creating a secure encrypted internet session, or SSL VPN. All modern web browsers support TLS. Now, I just mentioned Secure Socket Layer, or SSL. SSL is an older cryptographic protocol that is very similar to TLS. The most common use is in internet transactions. Why? Because all modern web browsers support SSL. But due to issues with earlier versions of the protocol, it has largely been replaced by TLS. SSL version 3.3 has been developed to address the weaknesses of earlier versions, but it may never again catch up to its cousin, the TLS protocol. Now that concludes this session on Networking Services and Applications Part 1. I talked about the basics of the virtual private network, and then I talked about the protocols used by the VPN network. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications, Part 2. Today we're going to be discussing network access services, and then we're going to move on to other services and applications. As always, there's a fair amount of ground to cover, so let's go ahead and dive into this session. I will begin with network access services. The first network access service that I'm going to discuss is actually a piece of hardware, the Network Interface Controller, or NIC. It can also be called the Network Interface Card. The NIC is how a device connects to a network. The Network Interface Controller works at two layers of the OSI model. At layer 2, which is the data link layer, it provides the functional means of network communication by determining which networking protocols will be used, as in a NIC that will provide Ethernet communication or a NIC that will provide point-to-point protocol. It also provides the local network node address through its burned-in physical media access control address. At layer 1, the physical layer, the Network Interface Controller determines how the network data traffic will be converted, a bit at a time, into an electrical signal that can traverse the network media being used, i.e., it provides the connection to the network. Most modern computers come with at least one built-in Ethernet NIC. Routers and other network devices may use separate modules that can be inserted into the device to provide the proper network interface controller for the type of media they're connecting to and the networking protocols that are being used. Another network access service is Radius, Remote Authentication Dial-In User Service. Radius is a remote access service that is used to authenticate remote users and grant them access to authorized network resources. It is a popular AAA protocol. That's Authentication, Authorization, and Accounting Protocol. It's used to help ensure that only authenticated end users are using the network resources they are authorized to use. The accounting services of Radius are very robust. The only drawback to Radius is only the requesters, the end users, password is encrypted. Everything else gets sent in the clear. Terminal Access Controller, Access Control System Plus, or TACACS Plus, Terminal Access Controller. Hello, I'm Brian Farrell, and welcome to PACE IT's session on DHCP in the network. Today we're going to be talking about static versus dynamic IP addressing. Then we're going to move on to how DHCP works, and then we will conclude with components and processes of DHCP. And with that, let's go ahead and begin this session. And of course, we begin by talking about static versus dynamic IP addressing. So how does a computer know what its IP configuration is? Well, more than likely, a computer received its IP configuration from a dynamic host configuration protocol server. Not only did the server give the PC an IP address, but it also told the PC where the default gateway was, and more than likely, how to find a DNS server. A computer will receive its IP configuration in one of two ways, either statically, which means manually set, or dynamically, which means through a service like DHCP. Static IP address assignment works fine for very small and stable networks, but quickly becomes unwieldy and error-prone as the network grows and more nodes come onto the network. So let's talk a little bit more about static IP addressing. The administrator assigns an IP number and subnet mask to each host in the network, whether it be a PC, router, or some other piece of electronic equipment. Each network interface that is going to be available to connect to the network requires this information. The administrator also assigns a default gateway location and DNS server location to each host in the network. Now, these settings are required if access to outside networks is going to be allowed. That would be through the default gateway, and if human-friendly naming conventions are going to be allowed. And that way you can more easily find network resources, and that would be through a DNS server. Now, each time a change is made, as in a new default gateway is established, each IP configuration on each host must be updated. That's why it becomes rather cumbersome and complicated as the network grows. Now, with dynamic IP addressing, the administrator configures a DHCP server to handle the assignment process, which actually automates the process and eases management. The DHCP server listens on a specific port for IP information requests. Once it receives a request, the DHCP server responds with the required information. Now let's move on to how DHCP works. Here is the typical DHCP process. Upon boot up, a PC that is configured to request an IP configuration sends a DHCP discovery packet. Now, the discovery packet is sent to the broadcast address 255.255.255.255 on UDP port 67. The DHCP server is listening to that port. It's listening for that discovery packet. When the DHCP server receives the discovery packet, it responds with an offer packet, basically saying, hey, I'm here to help. Now the offer packet is sent back to the MAC address of the computer requesting help, and it's sent on port 68. Once the computer receives that offer packet from the DHCP server, if it's going to use that DHCP server, it returns a request packet. That means it's requesting the proper IP configuration from that specific DHCP server. Once the DHCP server receives the request packet, it sends back an acknowledgement packet. Now this acknowledgement packet contains all of the required IP configuration information. Once the PC receives the acknowledgement packet, the PC changes its IP configuration to reflect the information that it received from the DHCP server. And that's the typical DHCP process in a nutshell. Now let's talk about components and the process of DHCP. We're going to begin by talking about the ports used. Now I already mentioned this once, but I'm going to mention it again because you need to know this. The PC sends its discovery packet out on the broadcast address 255.255.255.255 on port 67. That's UDP port 67. When the DHCP server responds, it responds to the PC's MAC address, Media Access Control address, on UDP port 68. That's important to remember. The PC uses UDP port 67. The DHCP server responds on UDP port 68. Then there's the address scope. The address scope is the IP address range that the administrator configures on the DHCP server. It is the range of addresses that the DHCP server can hand out to individual nodes. There's also what are called address reservations. Now these are administrator configured reserved IP addresses. The administrator reserves specific IP addresses to be handed out to specific MAC addresses. Now, these are used for devices that should always have the same IP address, as in servers and routers. If you didn't do that, there is the possibility that your default gateway's IP address might change. Now, the reason we use address reservation is this allows these addresses to be changed from a central location instead of having to log into each device and change the IP configuration separately. Now, part of the DHCP process are what are called leases. The DHCP server hands out that IP configuration information, but it sets a time limit for how long that IP configuration is good. This is called the lease. So the parameters are only good for a specified amount of time. Now, the administrator can configure how long the leases are. There are also options that the administrator can configure. The first one that's pretty obvious is the default gateway location. There's also the DNS server address, and the administrator can configure more than one DNS server location. An administrator can also configure an option for the PC to synchronize with a time server. So the administrator can configure a time server address. There are many more additional options, but those are the big three that you should remember. Now, when a PC boots up, it does have a preferred IP address. That would be the IP address that it had the last time it booted up. Now, it can request that same IP configuration from the DHCP server. Now, the administrator can configure the DHCP server to either honor that preference or to ignore it. Now, under the right circumstances, a DHCP server isn't required to reside on the local network segment. Now, as a general rule, broadcast transmissions cannot pass through a router. But if there is not a DHCP server on the local network segment, the router can be configured to be a DHCP relay. When a DHCP relay, also called an IP helper, receives a discovery packet from a node, it will forward that packet to the network segment on which the DHCP server resides. This allows for there to be fewer configured DHCP servers in any given network, reducing the amount of maintenance that an administrator needs to perform. Now that concludes this session on DHCP in the network. We started with static versus dynamic IP addressing, and then we moved on to how DHCP works, and we concluded with components and processes of DHCP. Now, on behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to the DNS Service. Today we're going to be talking about DNS servers, DNS records, and we will conclude with a brief discussion on dynamic DNS. And with that, let's go ahead and begin this session. We're going to begin this session with a talk about DNS servers. Now, DNS is the process that maps human-friendly names, as in www.google.com, to their appropriate IP addresses. Without DNS, we would have to memorize all of the IP addresses that we wished to visit. Now, DNS stands for Domain Name System, and it's very structured in nature. If the local DNS server apparatus doesn't contain the needed record, it sends the request up the DNS chain until a positive response is received back. Now, this positive response gets passed back down to the original requester. Now, DNS does require that an FQDN, fully qualified domain name, is used in order for it to function properly. Now, an FQDN is the www.google.com. It's that naming convention right there. The www is the specific service that's being requested. The Google portion is the local domain that contains the specific service, and the com is the top level that contains the Google that contains the specific service. That is an FQDN. Now that we've got that covered, let's talk about the different levels of DNS servers. First off, there can be a local DNS server. This is the server on the local network that contains the hosts file that maps all of the FQDNs to their specific IP addresses in the local subdomain. It may be present or it may not be present. Then there are top-level domain servers, the TLD server. Now, these are the servers that contain the records for the top-level domains. Examples of top-level domains are .com, .org, .net, .edu, so on and so forth. Now, each of these servers contains all of their information for their respective domains, kind of. And what do I mean by kind of? Well, the TLD servers do delegate down to second-level servers their information. They do that to ease the load so that the TLD server is not overloaded. But the TLD server is the server that is responsible for maintaining the record. Then there's the root server. This is the server that contains all of the records for the TLD servers. So if you're looking for a TLD that is kind of unknown, you will actually go to the root server, which will then pass you onto the appropriate TLD. Then there are authoritative servers and non-authoritative servers. An authoritative DNS server is one that responds to a request, and that authoritative server has been specifically configured to contain the requested information. An authoritative response comes from a DNS server that actually holds the original record. So an authoritative response comes from the name server that's been specifically configured to contain that record. Then there are non-authoritative DNS servers. Now, a non-authoritative DNS server is one that responds to a request with DNS information that it received from another DNS server. A non-authoritative response is not a response from the official name server for the domain. Instead, it is a second or third-hand response that's given back to the requester. In most cases, when we send a DNS request, we get a non-authoritative response back. Now let's move on to the various DNS record types. The first record that we're going to talk about is the A record. Now the A record maps host names, or FQDNs, to their respective IPv4 addresses. Closely associated with the A record is the AAAA record, or quadruple A record. This maps the FQDN to its respective IPv6 address. Then there's the CNAME record. Now this maps a canonical name, or alias, to a host name. What that means is that you can have edcc.edu be the same as edc.org without having to maintain two sites. The edcc.org can be the canonical name for edcc.edu. This works in part because of the pointer record, the PTR record. It's a pointer record that points out to DNS that there is a canonical name. And finally, we have the MS record. Now, this record maps to the email server that is specified for a specific domain. It is the record that determines how email travels from sender to recipient. And now let's move on to dynamic DNS. Now, dynamic DNS, or DDNS, permits lightweight and immediate updates to a local DNS database. This is very useful for when the FQDN, or hostname, remains the same, but the IP address is able to change on a regular basis. Dynamic DNS is implemented as an additional service to DNS. And it's implemented through DDNS updating. Now, this is a method of updating traditional name servers without the intervention of an administrator. So there's no manual editing or inputting of the configuration files required. A DDNS provider supplies software that will monitor the IP address of the referenced system. Once the IP address changes, the software sends an update to the proper DNS server. DDNS is useful for when access is needed to a domain whose IP address is being supplied dynamically by an ISP, or Internet Service Provider. That way the IP address can change, but people can still get to the service that they're looking for. Now that concludes this session on the introduction to the DNS service. We talked about DNS servers, we moved on to DNS records, and then we concluded with a very brief discussion about dynamic DNS. Now, on behalf of PACE IT, thank you for watching this session, and I'm pretty sure I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT session introducing network address translation. Today we're going to be talking about the purpose of network address translation, and then we're going to discuss how network address translation works. And with that, let's go ahead and begin this discussion. Of course, we're going to begin by talking about the purpose of network address translation. Network address translation, or NAT, solves a very serious problem of how to route non-routable IP addresses. As a partial effort to conserve the IPv4 address space, the private IPv4 addressing spaces were developed. These address spaces were removed from the public IPv4 address space and made non-routable across public IPv4 networks. And this led to the problem. Being non-routable prevents that private IPv4 address from communicating with remote public networks. NAT very simply solves this problem. A router with NAT enabled will translate a private IP address into a routable public IP address. When the response returns to the router, it passes the response back to the device that requested it. So now that we've covered the purpose, let's talk about how network address translation works. And first off, we get to talk about the fact that there are two categories of NAT. First up is static NAT. With static NAT, each private IP address is assigned to a specific routable public IP address. This relationship is kept and maintained by the NAT-enabled router. When a device needs access outside of the local network, the router translates the local IP address to the assigned public IP address. And when the response comes back, the router will translate the public IP address back into a local one. Static NAT is not flexible and leads to some scalability issues. An individual routable IP address must be kept for every device that requires access outside of the local network. So as the network grows, you need to increase the amount of public IP addresses that are under your control. That gets kind of expensive and kind of complicated. They developed dynamic NAT to resolve some of that issue. With dynamic NAT, the NAT-enabled router dynamically assigns a routable IP address to devices from a pool of available IP addresses. When a device needs access outside of the local network, the router performs the NAT function. Only the public IP address comes from a reusable pool of public IP addresses. That private IP address is assigned the public IP address from the pool, and once outside access is stopped, the routable IP address goes back into the pool to be reused. As initially designed, dynamic NAT was more flexible than static NAT, but it still led to some scalability issues. As more network traffic required access to outside networks, the pool of available public IP addresses needs to increase, or outside access cannot be achieved. But thankfully, there is a solution to this. And that solution is called port address translation, or in Cisco terms, that would be NAT with PAT. PAT is a type of dynamic NAT that was developed to increase the scalability of network address translation. When a local network device requires access to a public network, the NAT-enabled router dynamically assigns the public IP address to the device with the addition of dynamically assigning a port number to the end of the public IP address. The router tracks the IP addresses and port numbers to ensure that network traffic is routed to and from the proper devices. PAT still requires a pool of public IP addresses, but the pool may only contain one public IP address, or it may contain several for a large private network. This is the preferred method of implementing network address translation for two reasons. First off, there's less public IP addresses that are required, and it makes it easier for an administrator to maintain. Now let's talk about NAT terminology, specifically about the types of addresses. And we begin with the inside local address, which is a private IP address on the local network. It is the private IP address assigned to a specific device. Then there's the inside global address, a public address referencing an inside device. The inside global address is the public IP address assigned to the inside device by the NAT-enabled router, allowing access outside of the network. Then there's the outside global address, which is a public IP address referencing an outside device. It is the public IP address assigned to a device outside of the local network. Then there's the outside local address, which is a private IP address assigned to an outside device. This is the private IP address assigned to the outside device by the NAT-enabled router on the interior of the local network so that the inside device can communicate correctly with the outside device. Now that concludes this session on introducing network address translation. We talked about the purpose of network address translation, and then we talked about how network address translation works. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 1. Today I'm going to be talking about the public switched telephone network, then I'm going to move on to broadband cable, and I'm going to conclude with a brief section on fiber optics. And with that, let's go ahead and begin this session. Of course, we begin with the public switched telephone network. Before I begin with the public switched telephone network, let's talk about what makes a WAN as opposed to a LAN. Well, as a general rule, if you own and control the line that the data is using to get from one place to another, you are not using a wide area network or WAN technology. On the other hand, if you are using a form of transmission that you don't own, as in you're leasing a line or you're paying for the use of it, then you are likely using WAN technology. One of the most common physical infrastructures used in WAN technology is the public switched telephone network, the PSTN, due to its widespread availability. Just about everybody has a telephone line being run to their house or to their building. An older technology, but still somewhat valid today for WAN technology, is dial-up. Now, dial-up utilizes the PSTN to transmit network traffic as an analog signal. Dial-up does require an analog modem to format the network traffic correctly so it can be transmitted. Your maximum theoretical speed on dial-up is 56 kilobits per second. It's not very fast. Then there's ISDN, Integrated Service Digital Network. ISDN is a digital point-to-point WAN technology that utilizes the PSTN. It's a completely digital service. It requires the use of a terminal adapter, or TA, to make the connection to the end nodes. This TA is often called a digital modem, but it's not. It's a terminal adapter. ISDN can use a primary rate interface, or PRI. Now, the PRI is composed of 23 64 kilobit per second B channels and one 64 kilobit per second D channel. That D channel is used for call setup and link management. A PRI can achieve 1.544 megabits per second speed, and that is commonly referred to as a T1 leased line. The most commonly implemented form of an ISDN, though, is the BRI, the Basic Rate Interface. It uses only 2 B channels and 1 D channel, and the BRI can achieve speeds of up to 128 kilobits per second. Now, ISDN is not as capable as a digital subscriber line, or DSL, but it can often be implemented where DSL cannot be installed. Speaking about DSL, let's move on to it. XDSL is the term for generic DSL. DSL is a digital WAN technology that utilizes the PSTN. DSL does require the use of a digital modem. It uses a dedicated digital line between the endpoint and a Class 5 central office, or CO. Now, in order for the most basic forms of DSL to be installed, you have to be within 18,000 feet of the CO. DSL is capable of carrying voice and data. When it does carry both, filters are put in place in order for the voice signal to come through without any interference. Now let's move on to the different types of DSL. And first up is symmetric DSL, or SDSL. Symmetric DSL is synchronous in nature. That means that the upload and download speeds are the same. SDSL does not carry voice communication. So if you need voice service, an additional line is going to be needed. SDSL is used by businesses that don't quite need the performance of a T1 leased line, but they do require the symmetrical upload and download speeds. More common than SDSL is ADSL, or asymmetric DSL. It's asynchronous in nature. That means that the upload speed is slower than the download speed. ADSL can carry data and voice. Common upload speeds for ADSL are 768 kilobits per second, with download speeds of up to 9 megabits per second. It is the most common implementation of DSL in the small office, home office environment. Last up for DSL is VDSL, or Very High Bitrate DSL. It's asynchronous in nature as well. It's used when high-quality video and voice over IP is necessary. VDSL is commonly limited to download speeds of 52 megabits per second with an upload speed of 12 megabits per second. That's a whole lot faster than ADSL. But VDSL is only possible when you're located within 4,000 feet of a central office. There is an exception to what I just told you, though. The current standards do allow for up to 100 megabits per second speed over the PSTN using VDSL, but in order to achieve that, you must be within 300 meters of the central office. Now that the PSTN is out of the way, let's move on to broadband cable. Broadband cable is coaxial cable networking. It's a broadband connection to a location delivered by the cable company. Broadband cable can deliver voice, data, and television all through the same connection. And the way it works is the digital signal is delivered to the head-end. This is where all the cable signals are received. The signal is then processed and formatted and then transmitted to the distribution network. The distribution network is a smaller service area served by the cable company. The distribution network architecture can be composed of fiber optic cabling or coaxial cabling and or a hybrid fiber coaxial cabling, or HFC. Unlike DSL, the bandwidth of the distribution network is shared by all of those who connect to it. This can lead to increased latency and congestion during busy times. The final distribution to the premise is usually through a coaxial cable. The other thing that you need to know about broadband cable is that all cable modems and similar devices must measure up to the ISP's required Data over Cable Service Interface Specification, or DOCSIS specification. If it doesn't measure up, you're not going to achieve the speeds that you expect. Now let's conclude with fiber. Fiber optic networking is using light to transmit data and voice. This allows for more bandwidth over greater distances. Fiber optic networking is more expensive to install, but is also less susceptible to line noise. The fiber synchronous data transmission standard in the United States is called the Synchronous Optical Network, or SONET standard. The international standard is called the Synchronous Digital Hierarchy, or SDH. Both SONET and SDH define the base rates of transmission over fiber optic cabling, which are known as optical carrier levels. Dense wavelength division multiplexing is a method of multiplexing several optical carrier levels together, up to 32 of them, into a single fiber optic cable, effectively increasing the bandwidth of that single optical fiber. Instead of DWDM, you could use CWDM, coarse wavelength division multiplexing. It's similar to DWDM, but it only allows for up to 8 channels on a single fiber. When fiber optic is delivered to the premise, it's usually delivered over a passive optical network, or PON. A PON is a point-to-multipoint technology that uses a single optical fiber that's used to connect multiple locations to the internet. The passive optical network uses unpowered optical splitters. Now that concludes this session on WAN Technologies Part 1. I talked about the public switched telephone network, then we moved on to broadband cable, and I briefly ran through fiber optic networking. On behalf of PACE IT, thank you for watching this session, and I'm looking forward to doing another. Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 2. Today we're going to be discussing GSM and CDMA WAN connections. Then we're going to move on to WiMAX WAN connections, and we're going to conclude with satellite wide area network connections. There's a fair amount of information to cover, so let's go ahead and begin this session. And of course, I'm going to begin with the GSM and CDMA wide area network connections. All cellular carriers use one of two methods for connecting devices to their networks, and those methods are not compatible. Currently in the United States, AT&T and T-Mobile use the Global System for Mobile, or GSM standard, to connect their devices to their networks. Both Sprint and Verizon use Code Division Multiple Access, also known as CDMA, as their method of connecting to networks. And those two standards are not compatible. The majority of the rest of the world utilizes GSM as the method for cellular network access. Let me speak briefly about cellular networking. Cellular networking involves using the cellular phone system for more than just phone calls. Cellular networking has been around for a while, and it originally wasn't known as this, but the first version of it is First G or 1G cellular, and it was only capable of voice transmissions. As improvements came along, we got 2G. That is cellular with simple data transmission capabilities, as in text messaging. 2G Edge offered some basic cellular networking connectivity and was a stopgap measure between 2G and third generation cellular. 3G cellular is the beginning of cellular WAN networking. It's giving way to 4G cellular, which is still an emerging technology. 4G currently consists of both LTE and WiMAX. As a special mention, we need to talk about Evolved High-Speed Packet access, which is HSPA+. It was a stopgap between 3G and 4G networking. It's still available today. The current standard for HSPA+ allows for up to a maximum data rate of 84 megabits per second. Now, it's not quite as good as LTE, which is long-term evolution. LTE uses an all IP-based core with high data rates. Now, LTE is compatible with both 3G and WiMAX. The current standard for LTE allows for up to 300 megabits per second in download speeds and up to 75 megabits per second in upload speeds. Now let me introduce you to WiMAX WAN connections. WiMAX stands for Worldwide Interoperability for Microwave Access. That's a mouthful. That's why we say WiMAX. WiMAX was originally developed as a last-mile alternative to use when DSL or cable was not available. It can provide an alternative broadband connection to a fixed location. It uses microwave transmissions as an over-the-air method to transmit voice and data. It does require line of sight between relay stations. But WiMAX can be used to cover significant geographic distances. Also, many municipalities are exploring the use of WiMAX as a means of providing reasonably priced broadband to their citizens without having to wire every household. WiMAX is often considered to be a type of 4G technology because it is compatible with LTE networks. But WiMAX is not compatible with third-generation cellular networks. It is time for us to conclude with satellite WAN connections. Satellite WAN connections are a type of microwave satellite networking. It uses microwave transmissions as an over-the-air method of transmitting voice and data, just like WiMAX. It can be an effective means of extending networks into places that are hard to reach. It does use microwave radio relay as the method of transmitting data through the atmosphere. Just like WiMAX, it requires line-of-sight relay stations, but it can cover even more distances than WiMAX. Why is that? That's because it utilizes a satellite network. By the way, because of the distances that satellite transmissions can cover, this can lead to latency problems. Think about it. The signal's got to go from a terrestrial location up to the satellite, probably over to another satellite, and then down to another terrestrial station. That's a significant amount of distance, and there's going to be some lag. I just talked about the communication satellite. They're also known as ComSats. These do form part of the microwave relay network. ComSats can use a variety of orbits, including the malignant, geostationary, low polar, or polar orbits. The low polar and polar orbits are used to boost microwave signals before sending the signal back to Earth. Now that concludes this session on WAN Technologies Part 2. I briefly talked about GSM and CDMA WAN connections. Then I moved on to WiMAX WAN connections, and then we concluded with satellite WAN connections. Now, on behalf of PACE IT, thank you for watching this session, and I'm looking forward to doing some more. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 3. Today I'm going to briefly discuss Metro Ethernet WAN connections, then I'm going to move on to leased line WAN connections, and we're going to conclude with some common standards. And with that, let's go ahead and begin this session. Of course, I'm going to begin by discussing Metro Ethernet WAN connections. A Metro Ethernet connection is when the service provider connects to the customer's site through an RJ45 connector. The customer will view that WAN connection as an Ethernet connection, while in reality the type of connection will be dependent upon the level of service that has been purchased. The service provider may also use a variety of different wide area network technologies behind the scenes, but the customer will always view it as being an Ethernet connection. Metro Ethernet is commonly deployed as a wide area network technology by municipalities at the metropolitan area network or MAN level, as in at the municipal level. It's time for us to discuss leased line WAN connections. A leased line is a dedicated circuit or connection between two endpoints used for communication. When we're talking about IT, a leased line is usually a digital point-to-point connection. A leased line can utilize either a plain old telephone service line, a POTS line on the public switched telephone network, or it can be a fiber optic circuit provided by a telecommunications company. Leased lines tend to be more expensive for the customer as the circuit can't be utilized by any other entity. So the whole cost is borne by the customer because they're the only ones who get to use it. Most often, the speed of a leased line is limited by what the customer is willing to pay. There are some multiplexing technologies out there that can be used to increase the amount of channels that are provided on the connection. One of the leased line technologies that you need to know about is point-to-point protocol, PPP. It is a common data link layer or layer 2 protocol that's used with leased line networks. PPP can simultaneously transmit multiple layer 3 protocols. It can transmit IP and IPX and AppleTalk all at the same time through the use of control protocols, which are actually specific to the layer 3 protocol that's being transmitted. PPP can include a feature called multi-link PPP, which allows for multiple physical interfaces to be bonded together and act as a single logical interface. This effectively increases the available bandwidth to that system. There are different types of leased line connections. In the United States, Japan, and South Korea, there are T carrier lines. Each T line is composed of 24 digital signal channels. These are often called digital signal zero channels or DSO channels. Each channel is capable of carrying 64 kilobits per second. The 24 DSOs make up what is called a DS1 channel. In Europe, we have E carrier lines. Each E line is composed of 30 digital signal channels. These are also called DSO channels. The 30 DSO channels also make up what is called a DS1 channel. When we're talking about fiber optic speeds, we often talk about optical carrier lines, or OC lines. The OC data rates per channel are established by both the SONET and SDH networking standards. SONET is the United States standard and SDH is the international standards. Interestingly enough, the OC rates are the same across the two standards. It's possible to multiplex multiple channels into the same fiber using different methods. The first method is dense wavelength division multiplexing, DWDM. It allows for up to 32 separate channels on a single fiber cable. Or you could use coarse wavelength division multiplexing, which allows for up to 8 separate channels on a single fiber optic cable. Let's conclude with common standards. The standards I'm going to be talking about are the speeds. And we begin with T lines. A T1 is composed of 24 DSO channels, which are also known as a DS1, and it's capable of achieving speeds of up to 1.544 megabits per second. If that's not fast enough for you, you can lease a T3 line. It's composed of 28 T1 lines. Now, a T3 line is also known as a DS3, and it can achieve speeds of up to 44.736 megabits per second. If you're in Europe, you might lease an E1 line. An E1 line, which is composed of 30 DSO channels, can achieve speeds of up to 2.048 megabits per second. Just as with the United States, if that's not fast enough for you, you can lease an E3 line, which is composed of 16 E1 lines, which gives you up to 34.368 megabits per second speed. While a T1 is slower than an E1, a T3 is faster than an E3. For OC lines, we have the OC1. It's capable of 51.84 megabits per second in speed. Then there is the OC3, which gives you up to 155.52 megabits per second speed. It's becoming more common now to see OC12s. With those, you get up to 622.08 megabits per second. If you want gigabit type speed, you might consider leasing an OC48. That gives you up to 2.488 gigabits per second in bandwidth. Currently at the top of the line is the OC192. That gives you up to 9.953 gigabits per second speed. So essentially 10 gigabits per second worth of bandwidth. Now that concludes this session on WAN Technologies Part 3. I briefly discussed Metro Ethernet WAN connections, and then I went on to a discussion about leased line WAN connections, and then I briefly mentioned some common standards. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 4. Today I'm going to be discussing the difference between circuit switched and packet switched networks. Then I'm going to move on to a discussion comparing frame relay versus asynchronous transfer mode. And then we're going to conclude with multi-protocol label switching. There's a whole lot of ground to cover, not a whole lot of time. Let's go ahead and begin this session. Let's begin this session by talking about circuit switched and packet switched networks. Circuit switched networks have a dedicated circuit between two endpoints that is used for communication. While set up, the circuit can only be used for communication between those ends. Circuit switched networks are most common in networks with leased line communication channels. They're best used when there needs to be a fair amount of continuous data traffic between the two endpoints. And with circuit switched networks, there is only one path for the data to take. On the other hand, in packet switched networks, data is broken up into smaller chunks and moved through the network, only to be reassembled at the other end. The data is routed using the destination address, and the data may take different paths through the network that it's traveling through. As a general rule, packet switched networks are less expensive to maintain. Why? Because the user doesn't have to maintain a dedicated circuit 24/7. They're only paying for what they're using. Now let's talk about the differences between frame relay and asynchronous transfer mode. Frame relay is a WAN technology in which variable length packets are switched across a network. Frame relay is less expensive than leased lines, but frame relay can be made to look like a leased line through virtual circuits or VCs. A frame relay network will track a VC using a data link connection identifier to identify the ends of the VC. There are two terms associated with frame relay that you should be aware of. The first is access rate. That is the maximum speed of the frame relay interface. The other term is the committed information rate, the CIR. That's the guaranteed bandwidth that a customer receives. So that's the minimum speed of that frame relay network. The access rate may be higher, but the customer is always guaranteed the committed information rate. Now let's talk about asynchronous transfer mode, also known as ATM. ATM is a WAN technology in which fixed-length cells are switched across a network. These cells are always 53 bytes long. ATM can handle real-time voice and video because it's very fast, but it has poor bandwidth utilization. The small cell size reduces the efficiency of the technology, but ATM is very fast even if it is inefficient. Common speeds on an ATM network are 51.84 megabits per second and 155.52 megabits per second. Let's conclude with multi-protocol label switching. The acronym for multi-protocol label switching is MPLS. MPLS is a topology that's growing in popularity. Why? Because it's scalable. Also, it is protocol independent. MPLS can be used to replace both frame relay switching and ATM switching. It can be used to packet switch both frame relay and ATM network traffic. This allows MPLS to be used with both frame relay and ATM technologies. MPLS is often used to improve quality of service and flow of network traffic. It uses a label edge router to add MPLS labels to incoming packets if they don't have them. The label edge router then passes those packets onto a label switching router or LSR router. The LSR forwards those packets based on their MPLS labels to their final destination. Now that concludes this session on WAN Technologies Part 4. I talked about the differences between a circuit switched and packet switched network. Then we moved on to frame relay versus asynchronous transfer mode, and we concluded with a brief discussion on multi-protocol label switching. On behalf of PACE IT, thank you for watching this session, and I look forward to doing some more. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Network Cabling Part 1. Today we're going to be talking about twisted pair network cabling, then we're going to talk about twisted pair network connectors, and then we will conclude with categories of twisted pair. I have a whole lot of information to cover, and I need to get through this quickly, so let's go ahead and begin this session. And we'll begin by talking about twisted pair network cabling. Most people are familiar with twisted pair cables because they are the standard in the modern LAN. They are what you see most often when you're looking at network cabling. Twisted pair cables are composed of 4 pairs of wires contained within an insulating sheath. Each pair of wires is twisted together to reduce electromagnetic interference, which is called EMI. The twist rates differ between the pairs to reduce crosstalk between the pairs, which is a type of EMI. The colors of the pairs of wires are always white orange orange, white blue blue, white green green, and white brown brown. Twisted pair network cabling comes in either unshielded or shielded twisted pair. That would be UTP or STP. The difference is that STP has an additional shield that is either wrapped around each pair of wires or around all 4 pairs of wires. That shielding reduces the opportunity for EMI or crosstalk, but it is more expensive and a little harder to work with because it's not as flexible. UTP, or unshielded twisted pair, is deployed in the network much more often than STP. There are also plenum and non-plenum types of twisted pair. Most twisted pair cabling is non-plenum grade, but building codes often call for plenum grade cable to be run in plenum spaces. Now, a plenum space is that area that is designed to assist in the airflow of a building for HVAC purposes. And most often, the plenum is that space between the false ceiling and the actual ceiling. Plenum cable is jacketed in either a fire retardant cover or in a low smoke PVC jacket. Plenum cables often have a polymer or nylon strand woven into the cabling or into the jacket to help take the weight of hanging cables. This reduces the chance for the cable to stretch, which can cause the pair or pairs of wires inside the jacket to break. Twisted pair is usually either a straight-through cable or a crossover cable, but it can also be used to create a rollover or console cable. A straight-through cable is used to connect different types of devices together, as in a computer to a switch or a switch to a router, while a crossover cable is used to connect similar devices together, as in a PC to a PC or a switch to a switch. The straight-through and crossover cable use different pinouts to achieve their connections. A rollover or console cable is often required to connect to the console port on a switch or a router. It is quite common for one end of the rollover cable to use an RJ45 connector, while the other end utilizes an RS232, also called a DB9 connector. So now that I've mentioned those connectors, let's go on to twisted pair network connectors. And we're going to begin with the RJ11. You don't see these very much in what we think of as networking, but you do see them all the time. The RJ11 uses a 6-position, 4-contact modular connector. That's a 6P4C modular connector. It can carry data or voice, and its common usage is voice communication, telephony. All of your telephone jacks are RJ11s. Then there's the RJ45. This is the one that we always think about when we think about networking with twisted pair cabling. It uses an 8-position, 8-contact, or 8P8C modular connector. It can carry data or voice, and its common usage is data networking, Ethernet. Then there's the RJ48C. It also uses an 8-position, 8-contact modular connector, 8P8C, just like the RJ45. As a matter of fact, it's often thought of as being an RJ45, but it's used as the terminating connector at the demarc point for T1 lines. And as I said just a moment ago, it's often confused with the RJ45, but the active pins are different. Then we have the UTP coupler, the unshielded twisted pair coupler. It's used to connect UTP cables back to back and still maintain adherence to industry standards. You might still come across a 66 block being used for network connections, but probably not. It's a punch-down block that was initially developed to terminate and distribute telephone lines in an enterprise network. So you might still see it for telephony, but it's getting a little bit harder to find it. It was also used in slower speed networks as it can handle data traffic that's rated for Cat3 cabling. Much more likely you'll find a 110 block. Now this is a punch-down block that was developed to terminate and distribute twisted pair network cabling. It's capable of handling the signaling requirements of the modern network. I mentioned the DB9 or RS232 connector earlier. Well, here we go. It is a 9-pin D-subminiature connector developed for asynchronous serial communication between nodes. It was a common type of connector between a computer and an external modem. And as I said earlier, it often makes up one end of the rollover cable. You might come across a DB25, also known as an EIA 232 or RS232 serial connector. It is a 25-pin D-subminiature connector developed for asynchronous serial communication between nodes, just like the DB9, only it was larger. It too provided a type of connection between a computer and an external analog modem, and it's even less common than the DB9. Now let's move on to categories of twisted pair. And we begin with Cat3. Cat3 was rated for up to 10 megabits per second speed, that's 10 base T networking, and it had a maximum distance of 100 meters. By the way, unless I specify, all twisted pair cabling has a max distance of 100 meters. That 10 megabits per second wasn't quite fast enough, so then we got Cat5. Cat5 is rated for up to 100 megabits per second speed. That's 100 base T networking. And that still wasn't fast enough, so they developed Cat5e. Cat5e is rated for up to 1 gigabits per second. That's 1000 base T. Now we have Cat6. Cat6 is rated for up to 10 gigabits per second. That's 10 gigabit Ethernet, or 10 GBE. And with Cat6, you can only get that 10 gigabits per second over a max distance of 55 meters. For some reason, they thought they needed to go more distance than 55 meters, so they developed Cat6a. It has the same speed ratings as Cat6, but it has a max distance of 100 meters, and you can still achieve that 10 gigabits per second networking. Now that concludes this session on network cabling part 1. I talked about twisted pair cabling, then I talked about twisted pair network connectors, and I concluded with the categories of twisted pair cabling. Now on behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on network cabling part 2. Today we're going to be talking about coaxial cabling and fiber optic cabling. There's a fair amount of ground to cover, so let's go ahead and begin this session. And of course we're going to begin by talking about coaxial cabling. Coaxial, or coax, cabling is one of the oldest Ethernet standards for network cabling. It was standardized in 1973. It's been used for baseband, carries just a single digital signal, and it has been used for broadband, carrying multiple digital signals. It is composed of a central conductor that is covered by an insulating layer, which is covered by an outer mesh or foil layer, which is then finished off with an outer insulating layer. That inner metal mesh layer helps to protect against electromagnetic interference, EMI. There are several different types of coax cable. There is RG58. It was used in 10-base-2 networking. It could span a maximum distance of 185 meters and had a 50 ohms impedance value. It's no longer commonly found in the modern network. Then there's RG59. It's commonly used to provide a broadband connection between two devices over a short distance. And it has a 75 ohms impedance value. And it's only used for short distances because it leaks its signal. It can't span very far. Then we have RG6, which is used for cable TV or broadband. Now the distance that RG6 can span varies, but it still has a 75 ohms impedance value. And it's commonly used to make the connection to a cable modem by the cable company. There are two basic types of coax cable connectors. There is the BNC, also known as the bayonet Neal-Councilman connector. You can also call it a bayonet connector. It is used with coax cabling, but is now considered obsolete. The connection from the cable to the device was achieved through a spring-loaded twist lock type of connector. A BNC coupler can also be used to connect two coax cable segments back to back. Much more common is the F connector. It's a threaded bayonet connector, and it's also used with coax cable. An F connector coupler can be used to connect two coax cable segments back to back. Now let's move on to fiber optic cabling. So now let me describe fiber optic cabling. First off, it's relatively expensive and harder to work with than with other types of network cabling. It's not as common as other types, either coax or twisted pair, in the LAN environment. But it can resist all forms of electromagnetic interference, and it cannot be easily tapped into. That means it's harder for people to eavesdrop on your network transmissions. It also can cover long distances at high speed. Fiber optic cabling is designated by fiber type, cladding size. By the way, the cladding is what the light bounces down, and its jacket size, that outer jacket that covers the cable. The size of the cladding and the size of the jacket are listed in micrometers. Most applications of fiber optic cabling require that the cables be run in pairs. One cable to send transmissions, one cable to receive transmissions. The type of connector used on fiber optic cabling can impact the performance of the transmission. There are two basic categories of connectors. There is the UPC, the ultra physical contact. This connector has a back reflection rating of around a negative 55 decibel loss. Then there's the APC, the angled physical connector, which has a back reflection rating of around a negative 70 decibel loss, making it the better performing connector. Now let's talk about fiber types. There's multi-mode fiber, which uses an infrared LED system to transmit light down the fiber. It sends multiple rays of lights down the cable at the same time. It is used for shorter fiber runs, under 2 kilometers. It is less expensive than the other type of fiber cabling. Then we have single mode fiber, SMF. It uses a laser diode arrangement to transmit light down the fiber. It only sends a single ray of light down the cable. Even though my diagram depicts it as going straight, it still bounces down the cladding, but there's only one of them. It's used for longer runs that require high speed, and it can span more than 40 kilometers. So now let's talk about fiber optic cabling connectors. And first up is the SC. That is the subscriber connector or the square connector. You can also call it a standard connector. An easy way to remember it is stick and click. It's a push-pull type connector. Then we have the ST, the straight tip. You can also think of this as stick and twist. It is a spring-loaded twist lock type of connector. There is also the LC, which can be called the local connector or loosened connector or little connector. It's a type of connector that uses a locking tab to secure the connection. Similar to the LC is the MTRJ, the Mechanical Transfer Registered Jack. It's a small form factor connector that contains 2 fibers and that also utilizes a locking tab to secure the connection. You might also find a fiber optic coupler. Guess what it does? It's used to connect 2 fiber optic cables back to back. Now that concludes this session on network cabling part 2. I talked about coaxial cabling and I concluded with fiber optic cabling. Now on behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Cabling Part 3. Today I'm going to be talking about media converters, and then I'm going to talk about some cabling tools that you should know about. And with that, let's go ahead and begin today's session. I will begin by discussing media converters. It is not uncommon to be in a situation where a network contains more than one type of cabling. This can lead to a situation where there's a desire to connect different types of media together in order to make a cohesive or single network. Thankfully, media converters are readily available. The issue of trying to connect these disparate types of transmission together mostly comes into play when you're trying to join a fiber optic transmission to a copper wire infrastructure. And that's actually represented in the types of readily available media converters that are out there. The most common media converters will connect single mode fiber to Ethernet, or multi-mode fiber to Ethernet, or single mode fiber to multi-mode fiber, and finally there is a fiber to coaxial cabling media converter. You need to be aware that these devices are out there to help you create a solid network. Now let's move on to cabling tools. So every technician should put some thought into the tools that are in his or her toolbox. It is often said that you get what you pay for, and that is very true with tools. While a good technician can get away with buying the most inexpensive tools, by spending a little more money for a better tool, that can often make the task easier and ultimately make the technician more efficient. But you also need to be aware that you can spend more money than is necessary and not utilize all of the features in a given tool. So you need to find that balance point between spending too much money and not spending enough money to become a really efficient technician. Now let's move on to the tools themselves, and we'll begin with crimpers. Crimpers are used to place cable ends on cables. They can be designed to work with a single type of cable, as in twisted pair, or with multiple types of cable. I've seen some crimpers that have been able to work with RJ11s, RJ45s, and with a coaxial F connector. Next up are wire strippers. Wire strippers are used to remove the insulating covers on wires and cables. Many are designed to just cut through the insulation without damaging the cable contained within that insulation. But some are also designed to cut all the way through the cable so that excess cabling can be trimmed. When you're using those to cut insulation, you need to be careful that you don't cut the underlying cable. Then there are punch-down tools. These are used to secure cable wires into punch-down blocks. A good punch-down tool will trim the ends at the same time as it places the wire in the punch-down block. Then there are cable testers. These are used to test cables for common problems, as in misconfiguration of the ends or incorrect pinouts. Cable testers will often test for the cable standard used, either the T568A or the T568B, or they can tell you whether or not you've created a crossover cable. Cable testers will test for shorts or breaks in the continuity of the cable. Some types of testers can also test for cable length and quality. These type of testers are called cable certifiers. Then we have the TDR, the Time Domain Reflectometer. Now this is a cable tester for copper cabling that can determine the length of a segment and the electrical characteristics of the cable. Also, a TDR can tell you where a break. Hello, I'm Brian Farrell, and welcome to PACE IT's session on network topologies. Today we're going to discuss what a topology is, then we're going to discuss peer-to-peer and client-server networking, and then we're going to talk about some common network topologies. And with that, let's go ahead and begin this session. So what is a topology? Well, a topology is basically a map that can be used to describe how a network is laid out or how a network functions. A network topology can be described as either being logical or physical. A logical topology describes the theoretical signal path, while the physical topology describes the physical layout of the network. And you should know that a logical and physical topology don't need to match. And with that, let's move on to peer-to-peer versus the client-server networks. So are these really topologies? No, not really. They don't describe the signal path or the physical layout of the network. But yes, they are topologies because they do describe how the network functions. So that's why they're here in this discussion. Now, in a peer-to-peer topology, the nodes control and grant access to resources on the network. No one node or group of nodes controls access to a single specific type of resource. There's no real server present. Each node is responsible for the resources it's willing to share. Now, a client-server topology differs. Network resource access is controlled by a central server or servers. A server determines what resources get shared, who is allowed to use those resources, and even when those resources can be used. Now, in the small office, home office, it's common to find a hybrid topology. That's where a combination of peer-to-peer and client-server networking is used. Now let's move on to some common network topology models. The first one we're going to discuss is the bus. The original Ethernet standard established a bus topology for the network, both logically and physically. And what I mean by a bus topology is the signal traveled along a predetermined path from end to end. It went from one direction to the other direction, and then it could come back. Now, as time went on, the bus developed some mechanical problems. That led to the development of different physical topologies. But the logical topology remained the same in order to maintain backward compatibility. So when we discuss Ethernet networks, the logical topology is always a bus topology, while the physical topology can be different. So let's talk about the bus again. The signal traverses from one end of the network to the other. Now, a break in the line breaks the network. The ends of the bus line needed to be terminated in order to prevent signal bounce. And what that means is that if there was a break or the ends of the line were not terminated, when the signal got to the end, it would bounce back through and create a storm. In a bus topology, the network cable is the central point. Now, kind of related to the bus is the ring. It's a bus line with the endpoints connected together. A break in the ring breaks the ring. In a ring topology, it's common to use two rings, multiple rings, that counter-rotate. This safeguards against a break in one ring bringing down the whole network. Now, ring topologies are not very common anymore in the LAN, but they're still used in the wide area network, especially when SONET or SDH is used. Moving on from the ring, we have the star. The nodes radiate out from a central point. Now, when a star topology is implemented with a hub, a break in a segment brings down the whole bus because the hub retransmits out all ports. Now, when it's implemented with a switch, a break in a segment only brings down that segment. It is the most common implementation in the modern LAN. Then there's the mesh. A true mesh topology is when all nodes are connected to all other nodes. That's a full mesh. Now, those aren't very common because they are expensive and difficult to maintain. But it's common to find partial meshes. That's where there are multiple paths between nodes. Now, everyone knows at least one partial mesh network, and that would be the internet. Now let's move on to the point-to-point topology. That's where two nodes or systems are connected directly together. Now, if you're talking about two PCs, that's when they use a crossover cable to create a point-to-point topology. There's no central device to manage the connection. Now, this is still a common topology when implemented across a WAN connection, utilizing a T1 line. We also need to discuss point-to-multipoint. In a point-to-multipoint topology, a central device controls the paths to all other devices. This differs from a star in that the central device is intelligent. Now, wireless networks often implement point-to-multipoint topologies. When the wireless access point sends, all devices on the network receive the data. But when a device sends, its message is only passed along to the destination. It's also a common topology when implementing a WAN across a packet switched network. Now let's discuss MPLS. MPLS is multi-protocol label switching, and it is a topology that's used to replace both frame relay switching and ATM switching. It's a topology because it specifies a signal path and layout. MPLS is used to improve the quality of service and flow of network traffic. It uses label edge routers, LERs, which add MPLS labels to incoming packets if they don't already have them. Now, the LERs add the labels and pass the packets along to LSRs, label switching routers. These forward packets based on their MPLS labels. That's what makes this a topology. Now, that concludes this session on network topologies. We discussed what a topology is, Then we discussed the differences between peer-to-peer and client-server networking. And then I brought up some common network topology models that you should know. Now, on behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network infrastructure implementations. Today I'm going to be talking about design versus function, and then I'm going to talk about categories of different networks. And with that, let's go ahead and begin this session. Let's begin this session by talking about the difference between design and function. When describing a network, you have a couple of different options. Are you describing its design or its function? If you are going to describe its design, then the first place to start is to describe its topology. Is it a bus network? Is it a star network or a point-to-point? But if you're going to describe how the network functions, then the first place to start is to describe the category or infrastructure implementation of that network. And with that, let's move on to categories of networks. First up is the local area network, or the LAN. Most LANs are encompassed by a single network address range. That address range may be broken up into subgroups through the use of virtual local area networks, VLANs. A LAN can span anywhere from a small area, like a single room, to a whole building or a small group of buildings. The LAN tends to be the highest speed network. It is becoming more common to see 10 gigabits per second networking on the LAN. The most common types of network on the LAN are the 802.3 or Ethernet and or the 802.11 or wireless local area network. These are the most common types of network found on the LAN. Then there is the Metropolitan Area Network, or the MAN. It is larger than a LAN. Most often it contains multiple local area networks. MANs, or Metropolitan Area Networks, are often owned by municipalities. When a MAN is owned by a private entity, it is sometimes called a campus area network. Then there is the WAN, the Wide Area Network. Now, a WAN spans significant geographic distances. They can be described as a network of networks, and the best example of a WAN is the internet. So how do you tell when a MAN becomes a WAN? Well, as a general rule, if all of the infrastructure implementation has a single owner, then it is not a WAN. If it's large, it'll be a MAN, and if it's not quite so large, it'll be a LAN. But it's really easy to tell a personal area network, a PAN. Why? Because they are extremely distance and size limited. Most often, a PAN is a connection between only two devices. Common examples include a Bluetooth connection between a keyboard and a computer. That's a PAN. Then there are infrared or IR connections between a smartphone and a printer. That's a PAN. Another example of a PAN is near-field communication, which is now becoming seen between a smartphone and a payment terminal. The PAN tends to have low throughput of data and low power output. They don't consume a whole lot of power. As the distance between devices increase, the throughput on a PAN will decrease. Now a couple of special categories of networks. And first is the Supervisory Control and Data Acquisition Network, the SCADA network. Now a SCADA network is a type of industrial control system, or ICS, that is designed to control large-scale deployments of equipment. The controlled equipment is usually at more than one site. SCADA is often deployed in energy distribution systems by utility companies. SCADA uses a distributed control system, or DCS, to communicate with programmable logic controllers, PLCs, and or remote terminals to control the equipment and processes from a central location. So they have a central location to control equipment that's at remote locations. SCADA networks are often proprietary and often require additional training to understand them and to operate them. The last special mention on categories of networks is the MediaNet. It's a network designed and implemented specifically to handle voice and video. They are designed and implemented to remove quality of service issues like latency or jitter that can occur in other types of infrastructure. A video teleconference network, or VTC, is an example of a MediaNet. They are often implemented as its own infrastructure or as a sub-infrastructure of a larger network. That concludes this session on network infrastructure implementations. I talked about the differences between design and function of networks, and I concluded with a discussion on the different categories of networks. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to IPv4, Part 1. Today we're going to be talking about the purpose of IP addressing, and then we're going to move on to some IPv4 address properties. There's a whole lot of ground to cover, and we need to do it quickly, so let's go ahead and begin this session. Of course, we're going to start with the purpose of IP addressing. When Bob on Network A wants to view a web page hosted on a server on Network C, how does Bob's computer know where to send him? Well, somehow Bob has gotten that server's IP address, either in IPv4 format or IPv6. IP addresses are the location of a PC or server or some other network device that identifies it by both its network location and host location within that network. IP addressing provides a logical addressing scheme for our computers so that they can communicate on networks. Being logical means that the IP address can be changed with minimal fuss at any time, unlike the MAC address, or the Media Access Control address, which is physically embedded into the device. On the other hand, IP addresses are programmed and are easily changed. Now that we know the purpose of IP addressing, let's move on to some IPv4 address properties. IPv4 is made up of a 32-bit binary number. That means there are 2 to the 32nd power possible address combinations. That gives us 4,294,967,296 possible address combinations. With all of these possibilities, a process needed to be developed to keep everything neat and tidy, and, most of all, findable. The implementation of a subnet mask was the answer, and I'll get to that subnet mask in just a moment. Something that you will find useful is learning how to convert from binary to decimal. Now, decimal is base 2. That means there are only zeros and ones, as opposed to the base 10 that we're all used to dealing with. If you would like more information on how to convert from decimal to binary or binary to decimal, you can go to that website that's listed under this heading. So now let's talk about the initial properties of IPv4. It is a 32-bit binary number, as I said before. It's divided into 4 sets of 8, called octets. These are separated by periods, or decimals. Each octet is 8 bits, which equals 1 byte. We often represent IPv4 addresses in a human-friendly format that's called dotted decimal. Now, when we look at this address, 192.168.1.9, that is an IP address, but we don't know which portion is the network or which portion is the host. To be able to resolve this, it requires the use of a mask which determines or defines which portion is which. This mask is called the subnet mask, and the subnet mask has the same format as the IP address, as in it's 32 bits and it's represented in dotted decimal format. So let's take a look at how an IP address and subnet mask operate together. So we're going to begin with 192.168.1.9 with a subnet mask at 255.255.255.0. Now the 192.168.1.9 is the IP address, like I said, and the other portion, the 255.255.255.0, is the subnet mask. And it's easiest to show how the subnet masks by converting that dotted decimal back into binary. So we can do that by deconstructing the IP address. So the first octet would be 11 followed by 6 zeros. That equals 192. The second octet is 10101 followed by 3 zeros. That equals 168. That third octet's real easy. It's 7 zeros followed by a 1. And then we have the fourth octet, which is 4 zeros, a 1, 2 zeros, and a 1. That equals 9. Now if we deconstruct the subnet mask, what we have is we have 3 octets that are full of 1s and 1 octet that's full of zeros. That represents that 255.255.255.0. Now if we put the subnet mask under the representation of the IP address, anything that's not covered by a 1 in the subnet mask is a part of the host address. Everything that is covered by a 1 is the network address. So what we have for that IP address is that 192.168.1 is the network portion of the address, and the node portion of the address is the 9. And that's how the IP address and subnet mask work together to define the network and the node. Now that concludes this session on the Introduction to IPv4, Part 1. We talked about the purpose of IP addressing, and then we moved on to some IPv4 address properties. Now on behalf of PACE IT, thank you for watching this session, and I'm sure we'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to IPv4, Part 2. Today we're going to talk about classes of IPv4 addresses, and then we're going to move on to classless IPv4 addressing, and we will conclude with a brief discussion on subnetting IPv4 addresses. There's a whole lot of technical information to cover, so let's go ahead and begin this session. Let's begin by talking about classes of IPv4 addresses. Internet Protocol Version 4, IPv4, is a binary addressing scheme that's used for networking. It was initially finalized as a standard in 1981. IPv4 is a common network addressing scheme that is still being deployed today. There is an issue, though, with IPv4. Because of its structure and the growth and popularity of the internet, most of the world has run out of assignable IPv4 addresses. But thanks to some forethought, it's still a valid scheme today. We need to talk about classes of IPv4 addresses, and we begin with a Class A network address. Class A networks have an address range of 0 to 127 in the first octet. That gives us addresses from 0.0.0.0 up to 127.255.255.255. The first octet on the left has a binary representation that always begins with a 0. This gives us a possible 16,777,214 host addresses. And the subnet mask with a Class A network is always 255.0.0.0. Then there are Class B network addresses. They have an address range of 128 to 191 in the first octet. That means that Class B networks can have a range of 128.0.0.0 up to 191.255.255.255. The first octet on the left always has a binary representation that begins with a 10. Now, Class B network addresses give us a possible 65,534 hosts. And the subnet mask used with a Class B network is always 255.255.0.0. Then there are Class C network addresses, and they have an address range in the first octet of 192 up to 223. That means that we have an address range of 192.0.0.0 up through 223.255.255.255. And that first octet on the left always begins with a 110. Class C network addresses give us a possible 254 host addresses or node addresses. And the subnet mask with a Class C is always 255.255.255.0. The last class of address that you need to concern yourself with is the Class D network address. It has an address range of 224 up through 239 in the first octet, which means that it can range from 224.0.0.0 up through 239.255.255.255, and that first octet on the left has a binary representation of 1110. So the first 4 bits are always taken, and they are always 1110. Now, subnet masks are not defined for Class D networking. Class D network addresses are used for multicast communication. And finally, we have a special class of addresses. Well, kind of a class of addresses. And that involves automatic private IP addressing, a PIPA. In some cases, the Dynamic Host Configuration Protocol, DHCP, process may fail. In these cases, a node or host will self-configure an APIPA address. Now, with an APIPA address, the first 2 octets are always 168.254. And if you see that in your IP configuration, you know that you have a DHCP problem. So one of the first methods that they used to conserve the IPv4 address space was they broke them out into public and private IP addresses. Public IP addresses are routable. And being routable means that each public IP address is unique. There can only be one. Now, public IP addresses are not flexible. You are assigned to your network space. You're not really given a choice what your public IP address is going to be. And then there are the private IP addresses. These are non-routable. They do not need to be completely unique throughout the world. They only have to be unique on their network. The first one that we're going to discuss is the Class A license. There is only one Class A license. You have a possible address range of 10.0.0.0 up through 10.255.255.255. Next up is the Class B license. There are 16 possible network addresses, not network and host, but just network addresses available in a Class B license. They have an address range of 172.16.0.0 up through 172.31.255.255. And last but not least is the Class C license. There are 256 Class C licenses. with a possible address range of 192.168.0.0 up through 192.168.255.255. Now, private IP addressing is highly flexible. You get to assign the network space, it's not assigned to you. Now let's move on to classless IPv4 addressing. Now, the classes of addresses actually limited the flexibility of IPv4. Part of the reason for that was that the first routing protocols required the class structure. And you would think that with over 4 billion possible IP addresses that we'd still have flexibility, but we really didn't. Classless addressing, which is called classless interdomain routing, or CIDR, was developed to slow the growth of routing tables. It also slowed the exhaustion of IPv4 addresses. It also created much more flexibility. The subnet mask becomes fluid. It's not rigid with CIDR addressing. It does not affect the private address space ranges, though. Even though the subnet mask is now fluid, you still only have those range of addresses available. And with the introduction of classless addressing, subnetting is now possible and it's highly desirable. So let's take a look at how CIDR notation works. And we'll begin with 192.168.0.9 with a subnet mask of 255.255.0. What that becomes is 192.168.0.9/24. That /24 represents all of the ones in the subnet mask. And that's those first 3 octets on the left, the 255.255.255. And if you look at that address, it's a Class C address, which always has a 255.255.255.0 subnet mask, but it now becomes fluid with CIDR. We can take it and we can make it a 192.168.128.0/23. And what that really represents, that /23, is a subnet mask of 255.255.128.0. And that gives us a network of 192.168.128.0, which actually gives us a host range of 192.168.128.1 through 192.168.129.254. That gives us 512 host addresses as opposed to the possible 254. Now, the broadcast address for that network would be 192.168.129.255. So now let's move on to subnetting IPv4 addresses. So what is subnetting? Well, subnetting cuts address spaces into smaller pieces. It takes one range of addresses and splits it. This creates flexibility in network design and creates efficiency in address space utilization. So let's take a look at an example of subnetting. And this will involve a small office network. So originally, we have a network address of 223.15.1.0/24. This is a Class C private network, and it gives us a possible 254 hosts available. Why only 254? Well, because a host cannot be assigned to the network address, which is 223.15.1.0, and it can't use the broadcast address, which is 223.15.1.255. In this example, with this network address, all the hosts in the network can see all the other nodes. Now let's say that for security considerations, you want to split this into 2 networks. Well, you can do this using subnetting. So what you do is you take that /24 network and you create 2 /25 networks. And those would be 223.15.1.0/25 and 223.15.1.128/25. In this situation, the first network's host address range would be 223.15.1.1 up through 223.15.1.126. And why is that? Well, because you can't use the network address, which is 223.15.1.0, and you can't use the broadcast address, which is 223.15.1.127. The second address range that would be created through this subnetting process would give us a host range of 223.15.1.129 up through 223.15.1.254. That's because you can't use the network address, which is 223.15.1.128, and you can't use the broadcast address, which is 223.15.1.255. Each of those subnets would have 126 possible host addresses. So you took your possible 254 hosts available in one network and you broke it down so that you now have two separate networks, each that's capable of having 126 hosts. And that's an example of subnetting an IPv4 address. Now that concludes this session on the introduction to IPv4 Part 2. I talked about classes of IPv4 addresses. I then moved on to classless IPv4 addressing, and we concluded with a brief discussion on subnetting IPv4 addresses. Now, on behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the introduction to IPv6. Today we're going to be talking about the IPv6 address structure, and then we're going to move on to IPv6 network transmissions. And with that, let's go ahead and begin this session. Of course, I'm going to begin by talking about the IPv6 address structure. Now, IPv6 is the answer to the question of what do we do about running out of IPv4 addresses? Unlike IPv4, IPv6 will provide enough Internet Protocol, IP, addresses for the foreseeable future. Now, shortly after the creation of IPv4 and its implementation, the IANA, the organization that's tasked with assigning routable IP addresses, realized the available IPv4 address space would not be enough in very short order if nothing was done. The IANA then set about creating the replacement, and they initially started by working on IPv5. While they were working on IPv5, they found that due to the popularity of the internet, which was increasing at that point in time, that it wasn't going to be enough. So they scrapped IPv5 and began working on IPv6. Now the IANA is confident that IPv6 will function as the replacement for IPv4 for many decades to come. Why are they so confident? Well, we'll get to that here in just a moment. Now, IPv6 works at layer 3 of the OSI model, just like IPv4 does. Layer 3 of the OSI model is also known as the network layer, and its major focus is logical network and host addressing. IPv6's job is to provide logical network and host addressing to devices. IPv6 is a 128-bit binary addressing scheme as opposed to IPv4's 32 bits. The 128 bits are grouped together in sets, with each set being separated by a colon. Now each of these sets is 2 bytes long, and a byte is 8 bits. For human readability, the binary IPv6 number is converted to hexadecimal, that's base 16, with each hexadecimal number being equal to 4 bits. Now those 4 bits can actually be referred to as a nibble because it's half of a byte. An IPv6 address is 8 sets of 4 hexadecimal numbers, each being separated by a colon. That means that there are over 340 undecacillion addresses available to IPv6. That's 2 to the 128th power, which is roughly equal to 340 times 10 to the 36th power. See that number there? I'm not even going to begin to read that one to you. So now let's talk about IPv6's local address structure. For the local address, the first 64 bits on the left represent the local network, and the last 64 bits on the right always represent the host. The local address structure follows the EUI, or Extended Unique Identifier, format, specifically the EUI 64 format. For those hosts that have a 48-bit MAC address, that 48 bits is actually padded with an extra 16 bits to make it 64 bits in length. You can always tell a local address, which is also called the link local address, as it always begins with an FE80. With IPv6, every device gets both a local address and it gets a global address. Now the global address is unique. There is only one, and every device gets one. The host address is still always the last 64 bits, but every device actually gets assigned to a global network. The network portion is actually composed of a routing prefix and a subnet. This portion of the global address structure follows the classless interdomain routing, or CIDR, convention, with the number that follows the slash denoting the routing prefix. That's the part of the extremely global network that you belong to. The subnet is composed of the bits between the prefix and the EUI 64 host address. Global IPv6 addresses always begin in the range of 2,000 up through 3,999 in that first group of numbers on the left. Now, in most cases, the need for Dynamic Host Configuration Protocol, DHCP, has been eliminated. When implemented, IPv6 will auto-configure both the local and the global addresses that are required for their networks. When a device first comes online, it will use the Neighbor Discovery Protocol, NDP, to discover what the required network addresses are, both the local and global addresses. This allows devices to configure its own IPv6 address without an administrator's intervention. So let's talk about IPv6 notation. The 128-bit nature of IPv6 makes it cumbersome to write out, and it can take up unnecessary space. Because of this, some rules were developed to ease the burden and save space. When you're looking at a group of IPv6 numbers, any leading zeros in a set can be dropped. The thing to really remember about IPv6 is that only a single set of consecutive zeros may be replaced with the double colon. Why is that? Well, because if you could do it more than once, how would routers and other devices know how many zeros to pad in there? Even with this ability to shorten it, it's still difficult for us to remember IPv6 addresses, but it is still easier to write out, and it still conserves space within systems. Now let's move on to types of IPv6 network transmissions. And we begin with the unicast. Unicast is one-to-one communication. That is where a specific device is sending network traffic to another specific device. Unicast can occur on the local network, which remember always begins with FE80, or it can occur on the global network. Then there's multicast, which is one-to-a-few communication. With multicast, a specific device is sending network traffic to a specific group of devices that have registered to receive that traffic. Routers register to receive multicast transmissions that involve the routing protocols that they are programmed to use. With IPv6, multicast addresses always begin with an FF. Both IPv6 and IPv4 use both unicast and multicast transmissions. A unique type of transmission to IPv6 is anycast. Anycast is one to the closest communication. This is where a specific device is sending network traffic to a specific IPv6 address that has been assigned to multiple devices. The router only sends the communication to the closest one, at least from its perspective. Any cast transmission involves implementing DHCP v6. Earlier I said we really don't need to worry about DHCP anymore, but that's only partially true. While IPv6 is capable of auto-configuring its own local and global addresses, in certain situations that's not always desirable. DHCP v6 version 6 can be configured to hand out specific IPv6 addresses or duplicate IPv6 addresses when necessary. That's useful for when load balancing a network or when network redundancy has been created, or when you have a user that has a tablet, a cell phone, and a laptop, and you want to deliver the transmission to the closest device, the device that he's using at that point in time. That is where DHCP v6 comes in handy. IPv6 and IPv4 are not compatible, but we can do what's called a dual stack configuration. That's where the network and devices on the network receive both an IPv6 configuration and an IPv4 configuration. Or we can use what's called tunneling. There's 6-to-4 tunneling, which is used to encapsulate an IPv6 data packet in an IPv4 datagram, allowing that IPv6 packet to travel across or through an all IPv4 network. 6-to-4 tunneling can also be called Teredo tunneling. Now that concludes this session on the introduction to IPv6. I talked about the IPv6 address structure, and then I talked about IPv6 network transmissions. Now on behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on special IP networking concepts. Today I'm going to be talking about the media access control address, and then I'm going to talk about the difference between collision domains and broadcast domains, and we're going to conclude with types of network transmissions. There's a whole bunch of technical information to cover, so let's go ahead and begin this session. Let's begin the formal part of this session by discussing the media access control address. All networking interfaces come with their own special address already configured. That would be the media access control address, the MAC address. The MAC address is often referred to as the physical address or the burned-in address of the interface. While MAC addresses may be changed or spoofed, most often it's set by the manufacturer and never actually changes. Now, switches and other OSI Layer 2 devices rely upon that MAC address in order to get network packets to their correct destinations. The MAC address has a specific format. Actually, it has two specific formats. One is 48 bits in length and the other is 64 bits in length, and both of them are represented by hexadecimal numbers. Both formats can be broken down into two parts: the Organizationally Unique Identifier, or OUI, and the Extended Unique Identifier, the EUI. The Institute of Electrical and Electronic Engineers, the IEEE, assigns all electronic manufacturers their own OUI, which always makes up the first portion of the MAC address. Each manufacturer then assigns its own EUI to each device that is produced. Usually it is the serial number of that device. Theoretically, no two interfaces will have the same MAC address. I need to mention the EUI 64 format. IPv6 requires that the node address or the MAC address be in an EUI 64 format, so that MAC address has to be 64 bits in length. If the EUI of the interface is only 24 bits in length, it is actually split into two parts, and 16 bits of padding are added to create the EUI 64 format. Now let's discuss the difference between collision domains and broadcast domains. Before I can talk about collision domains and broadcast domains, I need to talk about carrier sense multiple access with collision detection. All Ethernet networks use this technology, also called CSMA with CD, when transmitting data. In an Ethernet network, all Ethernet devices have equal access to the network media and are capable of transmitting data at any time. This can lead to data collisions. With CSMA CD, a device listens to the carrier signal on the network media. If no other device is transmitting, the device is free to send data. If another device sends data at the same time, a collision is possible, which can corrupt the data. The devices listen for collisions. That's the collision detection part. If a collision occurs, the devices will stop transmitting and wait a random period of time before attempting to transmit again. To do this, they use what is called a back-off algorithm. With that out of the way, now let me explain what collision domains are. Collision domains are an area of the network where packets or network traffic can collide. There are some devices that break up collision domains. They can be broken up by switches, bridges, and routers, but not by hubs. On the other hand, a broadcast domain is defined as all the nodes that can be reached by a broadcast transmission. All the nodes that can be reached reside in the same network. Broadcast traffic cannot pass routers, so the domain is also defined by the subnet mask, and that subnet mask defines the network. Here's a special note. Technically, IPv6 does not use broadcast transmissions. IPv6 replaces broadcast transmissions with multicast transmissions. And what do you know? That's a good segue for us to discuss types of network transmissions. We're going to begin this section by talking about types of IPv4 network transmissions, and first up is unicast. Unicast is a specific source address transmission going to a specific source destination address. It can be thought of as one-to-one communication. It's only two devices transferring data between each other. Then there's multicast transmission. This is where a specific source address transmission is going to a set of registered destination addresses. This is one-to-a-few communication. Routers often use multicast transmissions to track their routes and to make changes to their routing tables. And finally, there are broadcast transmissions. This is where a specific source address transmission is going to all addresses on the local network. This can be considered as one-to-all communication, because all devices on the local network are going to be able to receive this broadcast transmission. So let's move on to types of IPv6 network transmissions. And IPv6 uses unicast, just like IPv4 does. IPv6 also uses multicast, just like IPv4. Where IPv6 differs is with anycast transmission. Anycast is where a specific source address transmission is going to a specific IPv6 address that has been assigned to multiple devices. The router uses an algorithm to determine which MAC address that has that specially configured IPv6 address is closest, and only that device receives the anycast transmission. Anycast can be considered as one to the closest communication. That concludes this session on special IP networking concepts. I talked about the MAC address. I talked about the differences between a collision domain and a broadcast domain. and then I concluded with a discussion on the types of network transmission. Now, on behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Routing Concepts, Part 1. Today I'm going to talk about the purpose of routing, and then I'm going to move on to some basic routing concepts. There's a fair amount of ground to cover, so let's go ahead and begin this session. First up is the purpose of routing. The basic purpose of routing is to connect different networks together to allow them to communicate and pass data traffic between them. Most often, routing protocols are how networks determine where to send network traffic. That's the routes that they will take. And these routing protocols build maps. Actually, they build routing tables, but we'll get to that later, that they use for directing network traffic. Routing is what makes this interconnected world function as well as it does. Networking would be pure chaos without it, as we'd have no idea where to send traffic. Now let's move on to some basic routing concepts. First up is static routing. Static routing uses administrator-defined routes. Each router in a static routing configuration must contain the route. A static route from router A to router B requires that router B has a static route back to router A in order for two-way communication to take place. If we had a static route from A to B and B didn't have one back to A could send traffic to B, but B could not send traffic back to A. Now, static routing is easy to set up in small networks, but it's not so easy to maintain. Networks change all the time. With static routing, when a change occurs in routers, the administrator has to go around to each router and implement that change. Then there's dynamic routing. This is where routers use protocols in order to determine the best route between two networks. The administrator determines which protocols will be used on the routers. In order for the routers to communicate, they must all be using the same protocols. There is an exception to that, and that's route redistribution. An administrator can configure a router to take one dynamic protocol and transform it into a different routing protocol to be used from that point on. This is the only case when routing protocols can be different across a network. Routing protocols can be stacked within a router. That means that there can be more than one dynamic routing protocol programmed into a router. Dynamic routing is very fluid and dynamic, and it's what makes possible today's interconnected world. The next concept is the default route. The default route is the direction that a router will send network traffic when there is no known route in the routing table. The default route is assigned by an administrator. It is usually a designated interface on the router, or it is the next designated next hop interface. Then there is the routing table. The routing table is a list of known routes to all known networks from the router's perspective. It is established by an administrator when static routing is used. It is dynamically built by routing protocols when dynamic routing is employed. Each routing protocol maintains its own routing table. Different routing protocols may have different routes to the same network. The loopback interface is an administratively configured logical number assigned to a router to ease administrative functions or routing processes. Often the loopback interface is assigned in an IPv4 address format even when IPv4 isn't used on the router. Many routing protocols have been designed to take the loopback interface into account when performing administrative functions. The loopback interface may be completely logical, or a physical interface may be assigned to be the loopback interface. Let's move on to routing loops. A routing loop is a possible problem that can be created if interconnected routers have a breakdown in their routing algorithms. When a routing loop occurs, network traffic keeps looping through the routers until some system or mechanism breaks the cycle. Routing loops can create network congestion or even bring down a network. Routing protocols use multiple methods to prevent routing loops from occurring. One of the main methods that they use is what's called the time to live field, or the TTL field. The TTL field keeps track of how long that packet has been in existence and how far it has traveled, and after a specified amount of time or distance, it will inform the next router to drop it. This helps to prevent routing loops. That concludes this session on the Introduction to Routing Concepts, Part 1. I talked about the purpose of routing, and then I moved on to some basic routing concepts. Now, on behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Routing Concepts, Part 2. Today I'm going to be talking about routing metrics, routing aggregation, and then I'm going to conclude with a brief discussion on high availability. We have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about routing metrics. It is quite common for there to be more than one route available to a remote network. Routing protocols use metrics to determine which route is the best route to reach those remote networks. Each routing protocol will use its own set of metrics in determining which routes to which networks are placed in its routing table. The same basic metric may be used by different routing protocols, but when this occurs, the metric is usually implemented in a different manner through the use of different algorithms. The first metric that we're going to discuss is the hop count. The hop count is the number of routers between two endpoints. This is determined from the sending router's perspective. The maximum transmission unit, or MTU, is another metric that is used by routing protocols. The MTU is the maximum allowed size of a packet measured in bytes that's allowed through an interface. The standard MTU for Ethernet is 1500 bytes. Packets that exceed the MTU must be fragmented into smaller pieces, leading to more packets, leading to a slower connection. Bandwidth is another common routing metric. Bandwidth is a measure of the speed of the network connection. The speed is commonly measured in either kilobits per second, megabits per second, or gigabits per second. Another common metric is latency. Latency is a measure of time that a packet takes to traverse a link. When latency is implemented by routing protocols, the total amount of latency or delay to go end to end between 2 points is what is used in the metric. The administrative distance, or AD, is probably the most important metric that's used on routers. The administrative distance is the believability of a routing protocol's advertised routes. Different routing protocols are considered to be more believable or trustworthy than others. Routers use the AD to help determine which routing protocol to use when more than one protocol is installed on the router. The lowest AD of an advertised route will determine the protocol that's used. There are some common standard administrative distance. First up is the directly connected route. That's a direct link between two routers. That has an AD of 0, and it is the most believable or trustworthy of routes. Next is the statically configured route. It has an AD of 1. External Border Gateway Protocol has an AD of 20. It's still fairly trustworthy. Internal EIGRP has an AD of 90. It's not as trustworthy as BGP, but it is more trustworthy than OSPF, Open Shortest Path First, which has an AD of 110. ISIS has an AD of 115, so not quite as believable as OSPF, but more believable than RIP, which has an AD of 120. External EIGRP has an AD of 170, and internal BGP, and I've never seen internal BGP used, has an AD of 200. Now, if you see an administrative distance of 255, that means that that route is not believable at all. As a side note, the AD can be set by an administrator. So if you are running both OSPF and ISIS on a router, but you want ISIS to be used, you could actually set OSPF's AD to a higher number than ISIS, and then ISIS would always be used before OSPF. Now let's move on to route aggregation. Without some mechanism put in place, routing tables would soon become very large and highly inefficient. Through careful planning, network administrators use a process called route aggregation to condense the size of routing tables. They do so through the use of classless interdomain routing, CIDR, to summarize routes to different networks. Route aggregation is common in networking. Let's take a look at an example of route aggregation. Suppose we have a router that has the following networks on its serial 0/1 interface. It has 10.1.1.0/24 known on that interface, 10.1.17.0/24, 10.1.32.0/24, and 10.1.128.0/24. All of those networks are known to that interface, that S/0/1 interface. These routes are what are known as contiguous routes. They're all in a line. They can be summarized or aggregated by a common CIDR entry in the routing table. They could all be summarized by the following entry, 10.1.0.0/16. Now there is a warning about route aggregation. Route aggregation takes careful planning during the network design phase. That above example would not work if the serial interface 1/1 on that same router was connected to network 10.1.2.0/24, because that new network makes those networks on the 0/1 interface non-contiguous networks. All the known networks are no longer all in a row. This leads to the fact that the routes could no longer be aggregated or summarized. Let's conclude with a discussion on high availability. Part of a network administrator's job is to ensure that networks remain up and active for the maximum amount of time. In an effort to ensure that networks don't go down, administrators often remove single points of failure. A single point of failure in a network is the point where a single failure will cause the network to cease functioning. Network administrators often use high availability techniques in order to remove those single points of failure. An example of a high availability technique is the use of redundant links to outside networks. Hot Standby Router Protocol, HSRP, is a specific example of a high availability technique. HSRP is a proprietary Cisco method of creating a fault-tolerant link using 2 or more routers with connections outside of the local subnet. The 2 routers are connected together as well as having connections outside of the local network. a virtual IP address is created and shared between the two routers. Devices on the network are configured to use that virtual IP address as their default gateway for packets leaving the network. If a single router goes down, the link outside of the network is still available. Another high availability technique is Virtual Router Redundancy Protocol, VRRP. It is an IETF, Internet Engineering Task Force standard that is similar in operation to HSRP. That concludes this session on the Introduction to Routing Concepts, Part 2. I discussed some routing metrics, then I moved on to route aggregation, and I concluded with a brief discussion on high availability. On behalf of PACE IT, thank you for watching this session, and I look forward to doing some more. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Routing Protocols. Today we're going to be talking about some of the differences between interior and exterior gateway routing protocols. We will introduce some more routing concepts, and then we will end with routing protocols in themselves. There's a whole lot of stuff to cover, so let's go ahead and jump into this session. Let's begin with a comparison between interior and exterior gateway protocols. Interior gateway protocols, or IGPs, are a category of protocols used within autonomous networks. Autonomous networks are networks that you control or that are under the control of a single organization. The most popular IGP protocols are OSPF, Open Shortest Path First, and RIP version 2. That's Routing Information Protocol version 2. Now there is a special mention here, and that's ISIS, which is Intermediate System to Intermediate System. ISIS is popular with extremely large autonomous networks, like an ISP's, or Internet Service Provider's, network. Exterior gateway protocols, on the other hand, are a category of protocols used between non-autonomous networks. So EGPs are used between networks that are controlled by different organizations or entities. The most popular EGP protocol is Border Gateway Protocol. Now, it's not uncommon for organizations to have more than one network that they are routing traffic between. These are called autonomous networks. Some IGP routing protocols use an administrator-defined autonomous system number, or AS number, as one means of identifying which networks can directly communicate with each other. The autonomous system number is not a metric, but a means of identifying a network that might possibly accept another network's traffic. Something to remember is that the AS is only significant within autonomous networks and has no relevance outside of them. Now let's move on to more routing concepts. Routing protocols can be classified by how they perform their routing. Interior gateway and EGP routing protocols can be broken out into three other categories of protocols, which is designated by their main method of determining routes between networks. The first class of routing protocols are distance vector routing protocols. With distant vector routing protocols, the routes are determined by how many routers exist between the source and the destination. The efficiency of the links in the selected route is not taken into consideration. With distance vector protocols, periodically the whole routing table is broadcast out onto the network. Then there are link state routing protocols. Metrics are used to determine the best possible route between destinations. Doesn't really matter how many hops there are. Once the route has been established, these protocols then only monitor the state of directly connected links and only make changes to their routing tables when changes to the links occur. With link state routing protocols, only changes in link status are broadcasted. And finally, there are hybrid routing protocols. These use aspects of both the distance vector and link state routing protocols. Let's talk about the next hop. The next hop is the next router in the path between 2 points. The next hop is often designated by an interface address of the device that is receiving the data, or by that router's name, or by that router's location. The routing table is the database table that is used by a router to determine the best possible route between 2 points. Different routing protocols use different algorithms to place routes in the routing table. The next concept is convergence. Convergence can be thought of as steady state. Convergence is measured in the amount of time that it takes all of the routers in an autonomous system to learn all of the possible routes within that system. Faster convergence times. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Elements of Unified Communications. Today I'm going to be talking about unified communications, and then I'm going to move on to some unified communication concepts, and then I'm going to end with voice over IP. And with that, let's go ahead and begin this session. Of course, I will begin this session by talking about unified communication. Now, unified communications is not encompassed by a single product or device. It's a growing category in the enterprise network. Unified communication, or UC, is the set of products and services that attempts to provide a consistent single user interface and experience across different media types and different devices. UC allows a user to send a message from one type of media, as in email, and have that media received as a different type of media. That email could become a text message or a voicemail. So now let's talk about some unified communication devices. First up is the UC server. These are specialized servers, which quite often are virtual in nature, that are designed to implement unified communication solutions in the workplace. The UC servers work in conjunction with UC gateways. A UC gateway is a network device that is designed to translate between different signaling methods, as in a voice over IP gateway, which will translate an analog public switched telephone network voice signal into a signal that can be understood on the VoIP network. There are some other UC devices. Any device that can be used in the implementation of a unified communication solution is considered a UC device. They may include, but are not limited to, VoIP phones, email systems, video conferencing systems, and instant messaging networks. Now let's move on to some unified communications concepts. The first concept that we're going to discuss is presence. Now, presence is an indicator that is used to communicate the willingness or ability of a user to accept communication. Common presence statuses include available, online, offline, busy, and do not disturb. Presence services are an important service provided in UC solutions, as they will track the individual users across multiple devices and networks in real time through the use of multicast transmissions. Once a communication session has been established, multicast communication is dropped and unicast network transmissions are used. Another UC concept that you need to grasp is quality of service. Quality of service techniques are implemented to improve unified communication by managing network traffic. The most common implementation of quality of service is class of service, COS. COS is a quality of service technique that's used to manage network traffic by grouping similar types of traffic and assigning a network priority to that traffic. As in, unified communication traffic is given a higher priority than email. A 6-bit differentiated service code point, DHCP, is used in the IP header to establish the COS, or class of service. Now let's move on to voice over IP. VoIP is one of the most common implementations in a unified communications solution. Through the use of a presence service, calls can be routed to the correct location for where the user is at. Two important protocols used in voice over IP are Session Initiation Protocol, SIP, and Real-Time Transport Protocol, RTP. SIP has two purposes. First, it is used to establish a communication session between two endpoints. The other purpose is that once the session is completed, SIP tears down that connection between the two endpoints. During the communication session, RTP is used as the transport call, helping to provide that quality of service through COS to the endpoints. Now that concludes this session on the basic elements of unified communication. I talked about unified communications, then I moved on to some unified communication concepts, and I concluded with a brief discussion on voice over IP. Now, on behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on virtualization technologies. Today I'm going to be discussing the difference between a hypervisor and virtual machine manager. Then I'm going to move on to components of virtualization, and then I'm going to have a brief discussion on software-defined networking. I have a whole lot of information to impart, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with hypervisors and virtual machine managers. So what is the difference between a hypervisor and a virtual machine manager? The difference could be nothing, or the difference could be everything. Some people use the term hypervisor very broadly. They use it to refer to any of the software that is used to manage virtual machines. Others will differentiate between the two terms in this way. A hypervisor does not need a host operating system, while a virtual machine manager, or VMM, requires a host operating system such as Microsoft Windows, Apple OS X, or a Linux operating system, while the hypervisor can operate as its own operating system. With that covered, let's talk about some of the components of virtualization. First up is the virtual desktop. A virtual desktop is a virtual machine, or VM, that functions as a desktop. Now, any modern operating system can be run inside of a VM desktop. Multiple virtual desktops may be hosted on or from a single host system. Then there are virtual servers, which surprisingly is a virtual machine that functions as a server. Any modern server operating system can be used in a virtual server environment. Multiple virtual servers may be hosted on or from a single host. Guess what? There are then virtual switches, firewalls, and routers. These are virtual machines that fulfill the functions of the switch, firewall, and router. Virtual firewalls and routers are particularly effective when they are combined with virtual network interface controllers, or virtual NICs, and virtual switches to create virtual networks. Speaking of virtual networks, an important consideration for when designing a virtual network is how that virtual network is going to pass traffic to remote networks, or networks outside of the host system. Virtualization by its nature leads to either an open and highly scalable network or a closed self-contained system. It is possible to create a completely self-contained network with all of the virtual components and never have network traffic leave the host machine. But if there is a desire or need for that network traffic to pass beyond the host system, then that function needs to be specifically granted. A connection must be created between the host system's physical NIC and the virtual networking equipment to allow network traffic to pass through the physical host system. Next up, software-defined networking. Software-defined networking, or SDN, is the process of allowing the administration and configuration of a network to be done dynamically. With SDN, the administrator uses a front-end program to make adjustments to the network. This program sends the instructions to the networking equipment, which is then reconfigured to perform as the administrator desires. SDN can allow network administrators to dynamically adjust network performance without the need to log into each individual device that needs to be adjusted to achieve the desired performance. SDN is considered to still be an emerging technology, but SDN also works well for virtual networks and cloud computing. Now that concludes this session on virtualization technology. I talked about hypervisors and virtual machine managers. Then I moved on to a brief discussion on some components of virtualization, and I concluded with another brief discussion on software-defined networking. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on storage area networks. Today I'm going to discuss the justification for storage area networks, and then I'm going to talk about storage area network technology. And with that, let's go ahead and begin this session. Of course, I'm going to begin with justifications for storage area networks. There have been several factors that have led to the increased demand for data storage. One of them has been the dramatic decrease in the actual cost of data storage. It actually costs us less now for storage on a per gigabyte basis than it has in the past. What has happened is that as the cost of storage has decreased, the demand for storage has increased dramatically. Businesses are now generating and analyzing huge amounts of data in an effort to create a competitive advantage. Think big data. I'm sure you've heard about big data recently. Or this increase in data collection has led to an increased demand for storage capacity. Another factor is that as the demand for data has increased, it has needed to be more available, which means that there has been a need to be able to access that data from anywhere, and the accessibility is needed to be increased as well, including from non-standard devices. A storage area network, or SAN, can be a solution to the need for both storage capacity and high availability. There are several advantages to the storage area network. First off is scalability. The amount of data that is being generated today is huge. This has led to a need to store that data. The SAN is more scalable than other options. As your storage needs increase, the capacity of the SAN can be easily increased to meet that storage need. Then there's data availability. The demand has also increased for that data to be available at any time from anywhere, and a SAN can play a vital role in creating that accessibility. One of the most popular implementations of a SAN is to deploy it as part of a cloud computing solution. This increases the availability of that data that's being stored on the SAN. And finally, there's optimization. As the requirements to store data are removed from application servers, those servers can then be optimized to run those applications much more efficiently. At the same time, data storage is also optimized. It's time now to discuss some SAN technology. The storage area network, or SAN, and the network attached storage, or NAS, often get confused with one another, but they are different. The SAN is an actual network of devices that have the sole purpose of storing data efficiently. On the other hand, the NAS is a specifically designed network appliance that has been configured to store data more efficiently than standard storage methods. The difference is that a NAS is a data storage appliance that is placed on a network, while a SAN is a network of data storage devices. It is not uncommon for a SAN to contain multiple NAS devices. With all of that data storage capabilities, several technologies have been developed to ease the transmission of that data. The first one that we're going to discuss is fiber channel, or FC. Fiber channel is a high-speed network technology that was originally developed to operate over fiber optic cables only. Since its introduction, the standards have been modified to allow the use of copper cabling in conjunction with fiber optic cabling. Fiber channel is commonly used to connect to SANs. When fiber channel is implemented, it uses the Fiber Channel Protocol, or FCP, as its transport protocol to transmit SCSI commands. So it transmits small computer system interface commands to storage devices, as in the NAS appliances. So a SAN implements FCP as opposed to TCP as its transport protocol when fiber channel is used. Another technology that was developed was Internet SCSI, or iSCSI. iSCSI is an IP-based networking standard that is used to connect data storage facilities and SANs. iSCSI allows for SCSI commands and processes to take place over longer distances than the original SCSI implementation. Jumbo frames are also allowed within the SAN environment. Jumbo frames allow for greater throughput of data by allowing up to 9,000 bytes of data to be in a single frame. This can greatly increase the efficiency of a SAN. As a comparison, the standard frame on an Ethernet network can only be a maximum of 1,500 bytes. Now that concludes this session on storage area networks. I talked about the justification for storage area networks, and then I concluded with a brief discussion on some SAN technology. On behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Cloud Concepts. Today we're going to be talking about cloud classifications, and then we will conclude with different types of cloud computing. There's a fair amount of information to cover, so let's go ahead and dive right in. I will begin our session with a discussion about cloud classifications. Cloud computing is where the resources on the network are not actually physical in nature. They are provided to the end user virtually. Cloud computing can lead to a very fluid and dynamic environment, as the required resources are normally only provisioned or supplied as needed and are decommissioned or shut down once their use is done. Most often, these virtual resources are not owned by the company or user that uses them, but are provided by a service provider. While cloud computing is highly configurable and changeable, it does have some basic structures that are used in the classification of the type of cloud that is in use. The first classification of cloud computing that we're going to talk about is the public cloud. This is where systems can interact with services and devices within the public cloud and on public networks, like over the internet, and possibly with other public clouds. The public cloud is where the services that are provided are not just provided to a specific user, but are open for the public to purchase and use. Then there are private clouds. This is where systems only communicate with services and devices within a specific private cloud. A private cloud is essentially just that, private. The only users who have access to it are ones who are authorized to use it. The cloud classification can be hybrid. It can combine aspects of both the public and private clouds. And last up, there are community clouds. This is where cloud services are used by private individuals, organizations, or groups that have a common interest. Now let's move on to different types of cloud computing. Because of the nature of cloud computing, it is very configurable to the needs and desires of the purchaser of the cloud services. Purchasers have many options beyond the type of cloud services that they want to provision. They must also determine what type of service they are going to require, from the most basic of services to the most highly complex of services. The purchaser needs to have a plan going into cloud computing in order for it to be efficient and effective for them. So now let's move on to some of those services that cloud computing can offer. First up is software as a service. The end user purchases the rights to use an application or software without the need to configure the virtual servers that will deliver the application to them. It is usually delivered as a web app or web application, opened and used from within a web browser, but not always. If you have a subscription to Microsoft's Office 365, you are utilizing software as a service. Then there is platform as a service, or PaaS. The user is provided with a development platform for the creation of software packages without the need to configure the virtual servers and the infrastructure that delivers it. You are essentially renting server or computing power in order to develop your software packages. PaaS is more complex than software as a service. And finally, we have infrastructure as a service. This is where the end user is provided with access to virtual servers, configurable by the customer, and other virtual network resources. Their infrastructure is actually virtually provided to them. This creates a highly configurable environment in which customers can create the resources and the performance that they require. The end user supplies the software that's going to be used on the IaaS network, or they purchase it as an additional software as a service. As you could have guessed from that last statement, it's not uncommon for the type of cloud computing being utilized by an organization to be a mix. Some departments may rely upon and use infrastructure as a service, while the development team will only utilize a platform as a service. Part of the advantage of cloud computing is that the purchaser only needs to initialize and pay for resources as they are needed. In a private cloud situation, it is possible for an organization that is using it to actually own the cloud resources. If they do own the cloud resources, they may have it on-site, or they may pay to have those resources hosted off-site. That way they can offload the maintenance cost of maintaining those resources. Now that concludes this session on basic cloud concepts. I talked about different cloud classifications, and then I concluded with a brief discussion on types of cloud computing. Now, on behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on implementing a basic network. Today we're going to discuss plan the network and then configure the network. There's a fair amount of ground to cover, so let's go ahead and dive into this session. Of course, I'm going to begin with plan the network. So you need a simple small office, home office network? Great, just plug two PCs into a single hub and you have a very basic network. But does it achieve what you want? How do you know if you don't have a plan? A network plan is vital when implementing any network more complicated than the most very basic of networks. That plan should cover what you are hoping to achieve and how you are going to get there. In addition to your expertise, you are also going to need input from your end users. Nothing is quite so frustrating as delivering the network that you've planned and built and having the customer tell you that it is not what they wanted or needed. Let's talk about that network plan in a little bit more detail. The first thing that you should do is create a list of requirements. Now, in order to make that list, you need to define why the network is needed. That will help you to define what network features are required. Then you need to define the scope or size of the network. Once you have those, they will help to establish a budget to implement that network. Once you know why the network is needed and what features are required, then you can work on network design. In network design, you need to determine what equipment is needed to implement that network. Part of the design is also how the network will be organized and how shared resources will be placed on the network. When you're planning the network, something that you should also consider are compatibility issues. You need to know what standards are in use now and what standards will there be in the future. Included in those compatibility issues are, does any current equipment that is required need specific cabling or connectors in order to be installed? That is something that often gets overlooked. Your network plan also needs to deal with network cabling runs, your internal connections. How many node connections will be required and where? How will you plan for future expansion? That future expansion is more than likely going to require more internal connections. You should build in some tolerance for future expansion. Then you need to consider external connections. How will the network connect to the outside? Where will that WAN connection come into your building, and where will your equipment be placed so that it can reach those WAN connections? That is also part of the network equipment placement plan. Part of that plan also needs to consider if there is a wiring or equipment closet and where it's going to be located. If you do have a wiring or equipment closet, are there environmental considerations about placing the equipment in there? Is it too hot? Is it too cold? Is it too humid or is it too dry? You need to think about those things when you're placing your network equipment. Your plan should also cover how network security will be implemented. Are there specific types of firewall and placement considerations for those firewalls? Will virtual local area networks be required, and if so, how many? Also, how will your switch port security be implemented? All of these go into a successful network plan. Now let's talk about configuring the network. Here are some network configuration considerations for you. First up, how will your clients receive their Internet Protocol addresses, their IP addresses? Using static IP address configuration creates a higher level of security, but it's harder to manage. You could use Dynamic Host Configuration Protocol, DHCP, to automatically assign IP addresses from a pre-configured pool, but your security may be a little bit lower if you do so. If you do use DHCP, you might want to consider using MAC filtering. MAC filtering will only allow specified MAC addresses, that physical burned-in address, onto the network. It is an effective security measure, but kind of like static IP addressing, it can be difficult to control and manage, especially as the network grows. Something else to consider is that if a server will be hosted on the network that needs to be accessed from outside of that network, as in you're hosting a web server, then you're going to need a demilitarized zone, a DMZ. The DMZ is an area of the network in which outside connections are allowed while the internal network remains protected from that outside traffic. A DMZ will require a custom configuration of the firewall. In most implementations, 2 firewalls are used, but it's not necessary to use 2 firewalls. Talking about firewalls, firewall placement and configuration considerations are next. Most small office, home office WAN connection devices, as in their cable modems or DSL modems, include firewall services that are sufficient in most cases for those small, simple networks. But if a DMZ needs to be deployed, the best method is to introduce an additional router and firewall into the network, with the DMZ residing between the WAN equipment and the new router firewall combination. Another aspect of deploying a DMZ is that port forwarding should also be used at the router firewall level. Port forwarding is used to direct requests for specific resources, like a request for a web page, to the computer that has the resource. Let's move on to wireless network configuration considerations. The first thing to consider in a wireless network is the name of the wireless network. That's the Service Set Identifier, the SSID. Now, the SSID can be set to broadcast in the clear. Alternatively, the SSID can be set for the broadcast to be hidden. Some people consider hiding the SSID broadcast as a security measure, but it really doesn't work that way. It doesn't stop the broadcast, it only hides the broadcast. A packet sniffer can easily see those broadcasts, and those broadcast packets can be easily interpreted. So hiding the SSID is not an effective security measure, but it does make things a little bit more difficult. The next aspect of wireless network configuration that you need to consider is encryption. First off, I will say you need to have encryption on your wireless network. Not only that, but you need to turn it on. By default, wireless routers and wireless access points, WAPs, do not have encryption enabled. And at the minimum, your encryption type should be WPA2 personal. That's at the minimum. Some wireless network equipment comes with a service that is called Wi-Fi Protected Setup, WPS. And if it does, it's enabled by default. This should be turned off and not used, as it creates a weakness in the wireless network. Why is that? Well, because WPS can be easily exploited by an attacker. The network that you implement may not be exactly what you planned, so document any changes to the plan. Undoubtedly, during the process of implementing that plan, some changes will be introduced, some by you and some by request of the end user. Always document those changes to the plan and have the end user sign off on them. Then be sure to incorporate those changes into the final network documentation. Now that concludes this session on implementing a basic network. I talked about plan the network, and then I talked about configure the network. On behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on analyzing monitoring reports. Today I'm going to talk about baseline reports, and then I'm going to move on to just reports in general. I have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and jump into this session. And of course, I'm going to begin by talking about baselines. How do you know what constitutes good network performance and what indicates that an issue is about to happen? This is where baseline documentation comes into play. Baseline documentation provides a snapshot of the network when it is running efficiently, at least hopefully when it's running efficiently. Baselines are usually kept as a log file. At the minimum, baselines should be established on CPU utilization and network bandwidth utilization. You may also basemark other functions as you deem them to be relevant. Network administrators should perform periodic tests against the baseline to check to see if the baseline is changed. They will change over time. And in order for network administrators to know what constitutes good performance on their network, their baselines need to be current. You can use Window Performance Monitor to help establish the baselines for your network. Let's talk about some of the items that should be considered for baseline reports. First up is network device CPU utilization. Knowing the CPU utilization on a piece of equipment can help to determine when a network device is going to fail. If your CPU utilization is constantly at 100%, you know there's a problem. That problem may be that it's going to fail, or it may be that you need to install more network devices to take care of a growing network. But you won't really know that if you're not baselining the CPU utilization. Network device memory utilization should also be baselined. It can help to determine when it is time to expand the memory of a network device. A good item for baselining is bandwidth utilization. This can help to determine the overall health of a network. It can help to determine when network segmentation should occur. It can also help to determine if a network device is about to fail, particularly if it's creating a storm of data. Baseline utilization reports can help identifying when a security breach has occurred. You might want to consider baselining your storage device utilization. This can help to determine when storage utilization has become a bottleneck on the network, where your storage device is actually causing the network to slow down because there's too much data being pushed into it. Which means that baselining your storage utilization can help determine when to increase the storage capacity of that network. You might also want to baseline your wireless channel utilization. This can help to determine how saturated the wireless channels have become. Once it's been determined that your wireless channels are saturated, a new wireless access point can be installed to alleviate the pressure, and then you need to create a new baseline for wireless channel utilization. This baseline can also help to determine if there is unauthorized wireless access occurring on your wireless network, especially if there is utilization on a channel that is not supposed to have any utilization. Now let's move on to analyzing reports. Before we talk about analyzing reports, let's talk about log file management. Log files can accumulate data quickly, and unfortunately, some administrators only review log files after a major problem has occurred. In most situations, this is a case of too much information at the wrong time. Good administrators will set the proper reporting levels with their logging software. They won't be logging all that debug information, that level 7 information, unless of course they're actively debugging a system or application. Good administrators will review log files and compare them against their baseline documentation. They do this to find issues while the issues are still minor and before they become major. Log files should also be kept and archived in case there is a need for historical data. When you do archive your log files, you should follow the organization's data storage policy. Something to consider is that you may want to create running graphs of important metrics that are captured by log files. Graphing the data gives a quick visual reference, making it easier to spot issues and trends. Many logging applications give the administrator the option of creating those graphs easily and quickly, but then again, they don't do you any good if you don't review them on a regular basis. If you're having an issue with a router or link, one of the first things that you want to do is you want to run an interface report. Now, hello, I'm Brian Farrell, and welcome to PACE IT's session on Network Monitoring, Part 1. Today we're going to be talking about the why of monitoring, and then we're going to talk about tools to monitor the network. There's a fair amount of ground to cover, so let's go ahead and jump into this session. I'm going to begin with the why of network monitoring. How do you know what is going on in your network? Is it healthy or is it about to crash? Network administrators really hate to be surprised by failures in their networks, especially ones that could have been foreseen and therefore kept from happening. How do they keep from being surprised? Well, they enact a plethora of procedures and tools to monitor their networks and to keep track of how those networks are behaving. They do this to reduce the surprise element. Now that we've covered the why of network monitoring, let's talk about tools that you can use to monitor the network. One of the main tools that network administrators use to monitor their networks are log files. All operating systems offer a means of viewing events that occur to that specific machine. That also includes networking equipment. There have been some applications that have been developed to monitor systems and networks that also generate log files, among other actions that they can take. Log files can be used to help pinpoint when a problem occurred and to help narrow down the possible causes of that problem. Log files can also be used to help create a baseline of network behavior so that you know what to expect from your network. Log files can usually be classified as being systems logs, general logs, or history logs. As a general rule, log files are an after-the-fact means of monitoring the network, and they're not very good at real-time analysis. That's partially due to the sheer amount of information that log files can generate. It's just too difficult to keep track of that in real time. Now let's talk about some specific logging tools that you can use. The first one that I'm going to talk about is Event Viewer. It's not really a log file in itself. It comes with Windows Server and most other Windows operating systems, and this tool can be used to review Windows log files. The most important log files that you can view from Event Viewer are application, security, and systems logs. Application logs contain events that are triggered by the actions of an application. For example, if you have Live Update enabled, it will create log entries based on actions taken by Live Update. Then there are security logs. These contain events that are triggered by security events. For example, some logs are created for successful and unsuccessful logon attempts. Then there are systems logs. These contain events triggered by Windows systems components. For example, it will create an entry for when a driver starts or fails to start. In either situation, a log entry will be created. Now let's talk about a non-Microsoft log, and that would be syslog. Syslog was developed in the 1980s, and it provides devices that normally would not be able to communicate with a means of delivering performance and problem information to systems administrators. This permits there to be separation between the software that generates the message, the storage of that message, and the software that analyzes the generated message. This separation of function allows syslog to be highly configurable and has allowed it to continue to be a vital tool for monitoring networks even today. As a matter of fact, The Internet Engineering Task Force, the IETF, liked syslog so much that they standardized it in 2009. Syslog can generate log messages based on the types of services that are running, and it includes a severity level that ranges from 0, the most severe, up through 7, the least severe. Syslog can generate a lot of log messages. Most network administrators configure it so that they only get alerted when a minimum severity level has been reached. As a matter of fact, you almost never want to capture debug log events unless you are actively debugging an application or service, just because it generates so much information. Syslog can be configured so that network administrators receive their alerts via text message or SMS message, or by email, or they may even receive a voicemail message. Well, syslog is a cool tool. It's not the only one that's out there. There's also Simple Network Management Protocol, SNMP. SNMP is an application layer protocol used to monitor and manage a network's health. Network or systems administrators configure monitors, these are often called traps, on devices that view the operation of a specific item. As in, is that router's interface up or is that router's interface down? The monitors periodically communicate with a network management station, or NMS, through GET messages, that's GET messages, that the NMS sends out. The response from the monitors is stored in a management information base, or MIB, which is a type of log file. The administrator can custom configure the monitors with set messages sent from the network management station. When an event occurs, as in the interface goes down, the trap is tripped and the event is logged. SNMP, just like syslog, can be configured to just log the event, or it can be configured to contact the network administrator. SNMP gives network and systems administrators the ability to provide more real-time monitoring of a network's performance and health. Then there's Security Information and Event Management, SIEM. It's a term for software products and services that combine Security Information Management, or SIM, and Security Event Management, SEM. SIEM may be provided by a software package, a network appliance, or as a third-party cloud service. It is used as a means of monitoring and providing real-time analysis of security alerts. That is an example of the Security Event Management function, the SIEM function. It can also be used as a tool to analyze long-term data in log files. That's an example of the SIEM function, or the Security Information Management function. SIEM can be highly configured to the needs of the individual network. Now that concludes this session on Network Monitoring Part 1. I talked about the why of network monitoring, and then I briefly touched on some tools for monitoring the network. On behalf of PACE IT, thank you for watching this session, and I'm sure I'll do another one soon. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Network Monitoring Part 2. Today we're going to be talking about active network monitoring tools, then I'm going to move on to wireless monitoring tools, and we're going to conclude with environmental monitoring. We have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about active network monitoring tools. Port scanners are used to scan a network for open ports and protocols. The information that a port scanner gathers is vital information if you want to harden the network. Port scanners are a great method of finding vulnerabilities in the network infrastructure, allowing the network administrator to plug those vulnerabilities before they become a security breach. I do have to issue a word of caution. You should only use a port scanner on a network or system that you are authorized to scan. Port scanning is a possible sign of someone trying to breach a system and can lead to problems if you're not authorized to scan that system. You don't want to have to try and explain to an information security specialist why you were scanning their network if you're not authorized to scan it. A little bit different than a port scanner are applications that use interface monitoring or packet flow monitoring. These are usually deployed as an active software tool to monitor and analyze network traffic within a network segment. They're commonly called packet sniffers or protocol analyzers. They allow for an in-depth look at what traffic is on the network and may reveal security issues that the network administrator can then mitigate. They help to identify top talkers on a network segment. Top talkers are those nodes or applications that generate the most amount of traffic. Packet sniffers can help to identify top listeners on a network segment. A top listener is that interface or the interfaces that are receiving the most network traffic, or put another way, those interfaces that are utilizing the most bandwidth for receiving packets. This can help an administrator when they have determined that load balancing might be needed on the network. Microsoft Message Analyzer and Wireshark are examples of free packet flow monitoring tools. Now let's move on to wireless monitoring tools. And we're going to begin with the Wi-Fi analyzer. A Wi-Fi analyzer is a similar tool to a protocol analyzer, but only for wireless networks. It sniffs out packets on wireless networks and gives you statistics on those packets that it sees. It can check for bandwidth usage, channel usage, top talkers, top listeners, etc., just like a packet sniffer can. Wi-Fi analyzers can also identify networks by passively scanning the radio frequencies to determine where traffic is coming from. Given enough time, a Wi-Fi analyzer can also identify hidden networks, or those that you don't know about. A Wi-Fi analyzer can also infer non-beaconing networks based on data traffic over the radio frequencies. They may not be able to discover the SSID, but they can tell the network administrator that something is passing traffic there. Another type of wireless monitoring tool are wireless survey tools. They're most commonly used as a design tool for setting up high-quality wireless networks. When used in conjunction with mapping tools, the survey tools can help to establish the required amount of access points to get the proper amount of coverage, the ideal antenna placement, and the optimum amount of channel overlap. Wireless survey tools can also help to identify possible sources of radio frequency interference, or RFI. Wireless survey tools are often used to eliminate wireless network performance and security issues before they ever have a chance to occur. Let's move on to environmental monitoring. A network's health can be affected by more than just a network interface failing or a possible security breach. Network and systems administrators also need to be concerned about environmental factors. Some of those factors include the quality and quantity of electrical power being supplied to their equipment, and the amount of heat in the rooms that equipment is kept, and also with that, the humidity level. Power monitoring tools are systems and tools that can be used to evaluate the amount of and the quality of the electrical power being delivered to the system. They're often deployed with or alongside an uninterruptible power supply, or UPS. The monitor will issue an alert when an issue with electrical power has been identified, giving the network or system administrator a chance to rectify the problem before any equipment has been damaged. All electrical components are designed to operate within a specific heat range. Not only are they designed to operate within that heat range, but all electrical equipment will generate some heat while they're in operation. And the harder that equipment works, the more heat they will generate. This is where heat monitors come into play. The heat monitor allows an administrator to control the temperature levels before they become an issue. Humidity is another item that network administrators need to keep in mind. Too little humidity increases the risk of electrostatic discharge, or ESD, but too much humidity increases the risk of condensation on equipment, and your electrical components do not like that condensation. Humidity monitors allow administrators the ability to control the humidity level through the proper means before it becomes an issue. Now that concludes this session on Network Monitoring Part 2. I talked about active network monitoring tools, then I moved on to some wireless monitoring tools, and I concluded with a brief discussion on environmental monitoring. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Supporting Configuration Management, Part 1. Today I'm going to be talking about what configuration management is, and then I'm going to discuss some documentation. With that, let's go ahead and jump into this session. First up is configuration management. Why do we need configuration management? Because even fairly small modern networks can get very complex very fast. Configuration management, or CM, is a discipline that is used to evaluate, coordinate, approve, deny, or implement change in or to an IT system. Configuration management plays a vital role in any network beyond the most simplistic of small office, home office networks. It helps to ensure that the network runs efficiently and smoothly. Network administrators and support staff will play a vital role in developing and implementing any CM system or process. Now that you know what configuration management is, let's talk about documentation. Documentation plays a key role in any configuration management system that gets developed. In the CM process, documentation is used to help evaluate and plan proposed changes. Documentation is also used to help in asset management, network maintenance, and vendor evaluations. The documentation that is created will depend upon the complexity of the systems under consideration. However, even if your organization doesn't implement a true CM style, some documentation should still be kept to reduce the burden on network personnel and to ease administrative management of the network. Some of the documentation that should be kept include policies and procedures. Policies are a set of guidelines that establish how the network is to be configured and operated. They also set the expected behavior of the people within the organization. As a general rule, policies are put into effect at the mid to upper management level. Procedures, on the other hand, are a set of documents that detail how the policies are to be implemented. As a general rule, procedures are set by the management of the level that's affected by the policy, and they get down to the step-by-step process of how to do things. Asset management documentation should also be maintained. This covers a broad category of documentation that's often used to help in the change management process. Asset management documentation contains detailed information on what assets are present. It also includes the maintenance history for those assets. This documentation is often used to help track update and upgrade cycles. Physical network diagrams should also be kept. These are a map or diagram of all network devices and how they connect. A physical network diagram specifies the cabling, connectors, and physical cabling runs. It will also include cable management documentation, which is considered a subcategory of the physical network diagram. The cabling management documentation will contain a wiring scheme, which establishes the type of cabling and the connectors used. It also defines the allowed standards for wiring those cables. Your documentation should also include a logical network diagram. It's similar to a physical network diagram, but more detailed. It provides details on the IP address scheme, active ports, protocols that are allowed on the network, etc., etc. Your logical network diagram also details connected networks. So what local area networks are present, or which virtual local area networks are present, so on and so forth. Part of your logical network diagram also details IP address utilization. IP address utilization can greatly affect the efficiency and performance of the network by allowing you to know which LANs or VLANs have space on which nodes can be added. Your physical and logical network diagrams may be combined into a single document. Vendor documentation also plays a role in supporting configuration management. It covers a broad category of documentation that can include the approved vendor list, the vendor approval process, and purchase order documentation. There are some common vendor documents that you should know. First up is the Memorandum of Understanding, or MOU. This is an agreement between two or more organizations that detail how those organizations are to take some common course of action. It is also often referred to as a letter of intent. It is not legally binding, but it does often lead towards a binding agreement. Then there is the Statement of Work, or the SOW, the SOW. It's a detailed document that specifies what work is to be performed, the expected outcome or deliverables, and the timelines to perform the work. The Statement of Work is often a key document in project management. Included in some vendor documentation is a Master License Agreement, or MLA. This is a legal agreement between two entities in which one agrees to pay the other for the use of a specific piece of software or software package for a specific period of time. Often, instead of being called a Master License Agreement, it is referred to as just a license agreement. Last up is the Service Level Agreement, or SLA. It details the allowable amount of response time the vendor has to resolve an issue or problem. Most commonly, it is associated with a service contract. That concludes this session on Supporting Configuration Management Part 1. I talked about configuration management, and then I moved on to documentation. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Hello, I'm Brian Farrell, and welcome to PACE IT session on Supporting Configuration Management Part 2. Today I'm going to be talking about backups, and then we will conclude with a brief discussion on Bring Your Own Device. And with that, let's go ahead and begin this session. I will begin by talking about backups. Backups are an essential part of any configuration management system. That's because small changes in a network device's configuration can introduce unexpected consequences into that network. In addition, there is always the possibility of a failure of a key component, which can lead to the loss of data or functionality. Backups play a key role in recovering from unexpected consequences or from the failure of a key component. Backup schedules must be implemented, and periodic tests should be conducted to ensure that the backup process is working. There's nothing worse than installing a backup and finding out that you really backed up nothing. There are three basic types of backups. There is the full backup. All data on the targeted system is backed up. This is the slowest backup method with the highest storage requirements, but it does lead to the fastest recovery method. When recovering using a full backup, it only requires the last full backup file. Then there's the incremental backup. With this type, only new or modified files are backed up. This is the fastest backup method with the lowest storage requirements, but it also leads to the slowest recovery method. The recovery process with incremental backups requires the last full backup file and all of the incremental backup files. The middle ground is the differential backup. Only data that is changed since the last full backup is saved. The time to backup is moderate, and it requires a moderate amount of storage, but it also is the middle ground on the length of time for recovery. The recovery process requires the last full backup file and the last differential backup file. Something else that needs to be backed up are your configuration files of network devices. Once a network device has been configured and it's operating as expected, a backup of the configuration files and operating system should be done. This helps to speed up the recovery time in cases of equipment failure or when a change to the configuration has introduced unexpected consequences. Having the configuration file backups on hand means that you don't need to manually input it to recover in these situations. Now let's move on to bring your own device. BYOD policies, or bring your own device policies, allow employees to use their own personal devices on an organization's network. While the employees are happy that they get to use their favorite IT devices on the corporate network, IT departments aren't quite as happy about it. Why? IT departments are tasked with keeping a network safe, yet they have very little control over the devices that employees bring in. In some cases, bring your own device policies have led to the introduction of malware into an organization's network environment. This makes them very unhappy. They can implement network admission control measures, or NAC measures, in an effort to reduce the risk associated with BYOD policies and to introduce configuration management to those devices. Network admission control is a Cisco process. Microsoft uses a similar process, but it's called Network Access Protection, or NAP. While their names may be different, they still function in the same way. NAC includes more than just authenticating users and devices on the network. All of the devices that are requesting access to network resources are screened for the type of device that it is, the operating system that's used, including any updates that are present. NAC will also check for security software, making sure that it's up to date. NAC can also check for the presence of malware or other security vulnerabilities. In an advanced setup, if the device requesting the connection has been rejected, the device is then redirected to a remediation server, which attempts to resolve the known issues. So if the security software is out of date, the remediation server may try and bring it up to date and then allow that device to connect to the corporate network. That concludes this session on supporting configuration management part 2. I talked about backups and we concluded with a brief discussion on bring your own device. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the importance of network segmentation. Today we're going to discuss the OSI model and segmentation, and then we're going to conclude with reasons for segmentation. And with that, let's go ahead and begin this session. We will begin by talking about the OSI model and segmentation. So what is segmentation? Well, it's taking a single network or system and breaking it into smaller discrete units. This can be achieved physically or logically. There are many reasons why you might want to segment a network. Some of them could include to ease administrative tasks, to achieve performance gains, to increase security, or to comply with regulations. As I mentioned earlier, segmenting a network can be achieved physically or logically. And either way, it involves different levels of the OSI reference model. It can be achieved at layer 1, the physical layer. This is taking a single network and making it into more than one network through the use of cable runs and equipment. This is the most extreme example of network segmentation. Not only is this the most extreme example of segmentation, but it's also an example of physically segmenting a network. You can also segment a network logically at the data link layer, which is layer 2, or at the network layer, which is layer 3 of the OSI model. This is taking a single network and making it into more than one by logically dividing the network. The logical segmentation of a network takes the least amount of physical resources to achieve it. Now let's move on to reasons for segmentation. First up is compliance. Some rules and regulations require that certain data be kept separate and secure, as in the Payment Card Industry Data Security Standard, or PCI DSS. This requires that you keep customer information separate and secure from normal business information. Segmentation allows for the regulated data to flow across its own network, keeping it more secure. Another reason for segmentation would be for network performance optimization. As a network increases in size, the amount of data that flows through them usually increases. This can slow down the performance of the network. Segmentation breaks the larger network into smaller units, which can lead to an increase in performance on those segments. Related to network performance optimization is the creating of high-performance networks. Some applications require more bandwidth in order to perform at the desired higher level. Voice over IP, video teleconferencing, and media nets, which are all examples of streaming services, all perform better when they are on their own network segments. A major reason for network segmentation is to separate private from public networks. Organizations often allow the public to access the internet from their locations. These are places that offer free Wi-Fi. Segmentation allows this traffic to be kept separate from the private corporate traffic. Then there are legacy systems. Some organizations use systems that are considered critical to their operation, but are not capable of residing on modern networks. Segmentation allows the legacy system to reside on its own subnet and network without compromising its performance or the performance of the rest of the network. Then there are testing labs. The lab can be used to test new applications, operating systems, update patches, so on and so forth. If these tests occur on the main network, it is possible that this testing could inject a problem into the main system. Segmentation allows for the testing to occur in a secure, easily controllable environment. And finally, there's security. One of the main reasons for performing network segmentation is for security purposes. Segmentation allows network and systems administrators to more easily control the flow of data between systems. Segmentation also allows network and systems administrators to more easily control access to network resources, therefore creating more security. An example of segmentation for security would be honey nets. These are network segments that are created with the sole purpose of attracting any network attacks through the use of multiple honey pots. Honey pots are systems that are configured to be attractive to network attackers, helping to draw attackers away from the main network systems and into the honey net. The network segment of honeypots allows the main network to remain secure and gives network administrators an opportunity to study an attack, including the methods of entry, so that countermeasures can be developed to prevent future breaches. A system that should be segmented are SCADA systems, or Supervisory Control and Data Acquisition Systems. These are the most widespread of industrial control systems, or ICS. The industrial control system uses coded signals over communication channels to provide control of remote equipment. They're commonly used in industrial applications to monitor and control systems. Utilities often use SCADA systems to control their operations through the use of DCS networks. that is a distributed control system network. The DCS allows for the control of multiple SCADA systems from a single location. The StutNet virus was originally designed to attack SCADA systems and can spread through the DCS, leading to more damage from the virus. Segmentation of the distributed control system can limit the amount of damage caused by such a virus attack on industrial processes. Now that concludes this session on the importance of network segmentation. We talked about the OSI model and segmentation, and then I concluded with reasons for network segmentation. Now on behalf of PACE IT, thank you for watching this session, and I hope you watch another one soon. Good day, I'm Brian Farrell, and welcome to PACE IT's session on applying patches and updates. Today we're going to discuss patches and updates, and then we're going to conclude by talking about upgrading versus downgrading. There's a fair amount of ground to cover, so let's go ahead and begin this session. And of course we're going to begin by talking about patches and updates. Today's modern operating systems are very complex and are composed of tens of millions of lines of code. Even your network devices and appliances are very complex and have complex software packages and configurations. This complexity of the modern operating system has led to the necessity for updates, patches, and hotfixes. These are used to add features, fix bugs, and repair security holes as they become known. One goal of administrators is to keep systems as up-to-date as possible through the use of these updates, patches, and hotfixes, reducing the system's vulnerability and increasing its functionality while reducing maintenance costs. A patch is a small section of code that is used to either increase functionality or fix a problem within a software package. A patch will change the version of the software package in a minor manner, as in version 1.0.0 will become version 1.0.1. An update is a larger section of code that is used to either increase functionality or fix problems within a software package that become known after production. An update will change the version of the software in a more major manner, as in version 1.0.0 will become version 2.0.0. Or, using a Microsoft example, Windows 8.0 became Windows 8.1. A hotfix, which can also be called a vulnerability patch, is similar to a patch, but it is actually smaller than a patch. They are designed to be deployed to fix a very specific issue within an operating system or other software package. Hotfixes are usually issued to fix security problems that become discovered after the software package has been produced. A service pack is a cumulative Windows update package that contains all patches, updates, and hotfixes between 2 points of time. Microsoft releases service packs as a method of easing the installation of an operating system, helping to keep it current. You install the operating system and then you install the service pack. That way you don't have to download and install every patch, update, and hotfix. In most cases, it is possible to automate the patch and update process through registering the product with the vendor who created it. Microsoft's operating systems can be set to automatically check for updates, and it will download and install them if you configure it that way. Most hardware vendors offer the same type of service for firmware and drivers. In most cases, these services can also be set to just inform the system of the availability of patches and updates, allowing administrators to manually download and install them. In a production setting, all patches and updates should be installed and tested in isolation, as in on a test system in a testing lab, before they are installed on vital production equipment. This reduces the chances that a patch or update will bring down a system that is functioning all right but is in need of the patch or update. Now let's discuss upgrading versus downgrading. Quite often, it is highly desirable to install the latest patches and updates in order to keep systems running efficiently. However, sometimes issues arise with the installation of a patch or update, leading to problems that were not caught during the testing phase. This is where backups and downgrading come into play. Backup copies of all systems and configuration files should be maintained in order to downgrade or roll back to the previous version for when a problem occurs during the deployment of a patch or upgrade. Being able to roll back to a prior version is often easier and more efficient than trying to resolve a problem that was introduced with an update. Administrators should keep backup copies that include the base package of the operating system or software package, a backup of the system before the patch was installed, and a backup of the system after the patch was installed. All of these backups should be kept and maintained as per your organization's policy. Now that concludes this session on applying patches and updates. We started by discussing patches and updates and then concluded with a brief discussion on upgrading versus downgrading. On behalf of PACE IT, thank you for watching this session, and I'm looking forward to doing another one. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Configuring Switches Part 1. Today we're going to talk about unmanaged versus managed switches, and then we're going to talk about spanning tree protocol. There is a whole lot of information to cover, not a lot of time, so let's jump into this session. I'm going to begin by talking about unmanaged switches and managed switches. Before we begin discussing the differences between unmanaged and managed switches, let's talk switch basics. Most switches operate at layer 2, the data link layer, of the OSI reference model. What makes a switch is an application-specific integrated circuit chip, or an ASIC chip. It is used to make switching decisions in place of software. This allows switches to break up collision domains. This allows switches to run in full duplex mode, and this allows switches to make faster decisions than either bridges or routers. When a switch receives a frame on a port, it makes some simple decisions based on its media access control table, or its MAC table. It will make one of three decisions. It may decide to forward the frame. That is where the frame is directed out the port on which the destination MAC address resides. It may decide to filter the packet. That is where the frame is not directed out of ports which are not associated with the destination MAC address. The final decision that it may make is to flood the frame. The frame is flooded or sent out all of the ports on the switch except for the port on which it came in on. An unmanaged switch is a simple switch. Plug it in and it works. There is no method provided for configuration. The unmanaged switch is designed with ease of installation as its main attribute. Managed switches, on the other hand, can be configured through either the command line or a browser-based interface. Managed switches provide for a high degree of network customization and control. A managed switch can also be set up so that an administrator can monitor its performance remotely and use protocols such as SNMP to make some modifications to its configuration. Now let's move on to spanning tree protocol. Spanning tree protocol is a loop avoidance technology. A switching loop can occur on networks where there are multiple paths to reach destination MAC addresses. Digital Equipment Corporation created the Spanning Tree Protocol, or STP, to reduce the possibility of switching loops. The switches elect a root bridge to control the switched network. The switches will shut down ports that are not the best path to the root bridge, thus reducing the risk of loops. No network traffic can flow until after the STP process has taken place and a stable state has been achieved. This stable state is called convergence, and it can take a significant amount of time with STP, up to 50 seconds. After convergence, the STP selected switch ports send out Bridge Protocol Data Unit packets, or BPDU packets, to help maintain the stable state. All switch ports in an STP-enabled network can be in one of 5 states. First off, there is the disabled state. That is where the port is administratively shut down. It's not receiving packets, it's not sending packets, it's just completely disabled. Then there's the blocking state. In this state, the port will not forward packets, but it's still receiving BPDU packets and will drop all other frames. Then there's the listening state. In this state, the port will not forward packets, but listens to BPDU packets to make sure that no loops can occur in preparation for the next state. Then there's the learning state. In this state, the port will not forward packets, but it is learning all of the paths in the network. It is populating its MAC address table in preparation for the next state. The last state in spanning tree protocol is the forwarding state. In this state, the port will forward and receive all packets that are flowing across the network that are directed to that port. The IEEE liked STP so much that it created the 802.1d standard. This is their version of STP. All modern Layer 2 switches run the 802.1d standard by default. The slow convergence time of the 802.1d standard led to the creation of Rapid Spanning Tree Protocol, or RSTP, which is also known as the IEEE 802.1w standard. RSTP has a much faster convergence time than 802.1d. With RSTP enabled on all switches, a network can achieve its stable state in approximately 5 seconds. That's a whole lot faster than the up to 50 seconds with the 802.1d standard. But RSTP is not turned on by default on Layer 2 switches. It must be enabled by an administrator. Instead of 5 possible port states, RSTP defines 3 possible port states. The first of these states is discarding. In this state, the port may be administratively disabled, or it may be in a blocking mode or listening mode. The next state is learning. In this state, the port is populating its MAC address table in preparation for forwarding packets. And the final state is forwarding. In this state, the port is actively forwarding packets. Now that concludes this session on configuring switches part 1. I talked about unmanaged versus managed switches, and then I had a brief discussion on spanning tree protocol. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another. Good day, I'm Brian Farrell, and welcome to PACE IT's session on configuring switches part 2. Today we're going to discuss installation considerations, and then we're going to move on to configuring the switch port. There's a fair amount of ground to cover, so let's go ahead and dive into today's session. Of course, I'm going to begin with installation considerations. The first installation consideration is whether or not you need a managed or unmanaged switch. The business or enterprise network is more complex than the small office, home office network. A SOHO network may be able to get by with using one or more unmanaged switches and still operate adequately. But once beyond the level of a SOHO, more thought and planning is required, as unmanaged switches are no longer up to the job. You are going to need managed switches. There are multiple issues to consider when installing a managed switch, and it is wise to plan for those in advance to save both time and frustration in setting up a network. One of the first things to consider is if there will be VLANs, virtual local area networks. While switches may break up collision domains, they do not break up broadcast domains. But VLANs will. A virtual local area network takes a single network environment and creates smaller network segments by subnetting the network address range, effectively breaking up the broadcast domains of that network. VLANs are used in a switched network environment for a variety of reasons. To break up broadcast domains into smaller segments, just like I just said. Another reason to use VLANs is they increase security by limiting access to network resources. The administrator configures the VLANs and then assigns users, nodes, or ports to a specific virtual local area network. All managed switches do come with a native VLAN, which is determined by the manufacturer. This native VLAN is used to help manage the switch. VLAN traffic is allowed to cross switch ports as long as the VLAN information matches. So VLAN 2 can send traffic to VLAN 2, but VLAN 2 cannot send traffic to VLAN 3. VLAN traffic is allowed to cross switch ports as long as the VLAN information matches. It does this through the use of trunk ports. That means that VLAN 2 can send traffic across a trunk port to VLAN 2, but it cannot send traffic from VLAN 2 across a trunk port to VLAN 3. VTP, or Virtual Trunk Port Protocol, is a Cisco proprietary method of creating a virtual trunk port, which allows VLAN traffic to pass between switches and to automatically manage the VLAN environment. In order for different VLANs to communicate with each other, a router or some other layer 3 device must be installed on the network. The next consideration is, how is the switch going to be managed? Switches may be managed out of band. That means that no network connection is required. This is achieved through the use of the console port on the switch. The console port is a specific port on managed switches used to connect to and configure or manage a switch. A rollover cable may be required to make the connection to the console port. Security should also be set on console ports to prevent unauthorized access through that console port. Your other option for switch management may be to use in-band management. With in-band management, a network connection is used to manage the switch. One of the most common methods of allowed in-band management is through the use of virtual terminals, or VTY connections. The most common VTY connections are Telnet or Secure Shell Sessions, SSH sessions. Security should also be set if Telnet is allowed on VTY type connections. By default, SSH is a secured connection. If you determine that you're going to use in-band management, the next thing that you need to do is to establish a default gateway address. That default gateway address must be placed on an interface that belongs to the native VLAN, or the default virtual local area network. The default gateway on a switch is different than the default gateway on a router. On a switch, it is only used to manage the switch and not to pass other network traffic. As part of the setup and management of the switch, an administrator should configure which users and passwords are allowed to connect to the switch and what their level of access to the configuration is going to be. In-band and out-of-band management security settings may be different. Some users may be allowed in-band management access, while others are not, and vice versa. If authentication, authorization, and accounting protocols are used in the network, the switch must be configured to use them as well. With that done, let's move on to configuring the switch port. I'm not going to actually show you the commands for how to configure the switch port, but I'm going to give you the information that you need to consider when configuring the switch port. First up is speed and duplexing. Most modern switch ports can auto-negotiate both the speed of the link and the duplexing mode used. But in some cases, an administrator may be required to manually set both the speed and the duplex in order for a connection to occur. Speed and duplexing errors are the most common cause for a link not being established between a switch and a router or between switches. Next up is VLAN assignment. All switch ports will belong to a VLAN, and that VLAN will either be an administrator configured one or it will be the native virtual local area network. As a side note, the native VLAN can be administratively changed, which should be done to increase the security level on the switch. Then there's trunking. Trunk ports are switch ports that are designed to carry VLAN traffic between switches. The standard protocol used is 802.1q. 802.1q strips off the VLAN tag. Actually, it changes that tag to match the native VLAN, which allows the traffic to cross over the port, and then once on the other side, then the 802.1q port on the other side reinserts the original VLAN tag. And that is trunking in a nutshell. You might want to consider port bonding using LACP. That's Link Aggregation Control Protocol. It is a protocol that is used to create a single logical channel from redundant connections between switches. So it bonds those ports together. This will increase the bandwidth between the switches. Now we're going to talk about PoE. Not Edgar Allan Poe, but Power over Ethernet. Some switches come equipped with Power over Ethernet ports, or PoE ports. These ports can use one of two methods to provide current over the network cable, as well as carrying data, allowing these ports to power small network devices while at the same time communicating with them. The port itself may provide the current, or the port may allow the use of a power injector to provide the power instead of the port itself. There are multiple PoE standards in place. The two most common are actually the PoE standard, the 802.3AF, which can provide up to 15.4 watts of current, or the PoE Plus, which is 802.3AT, which can provide up to 30 watts of current. Port mirroring may also be enabled on a switch port. This allows the configured port to receive all network traffic going to and from a specific port. By using port mirroring, an administrator can examine and analyze the traffic going into and coming from a specific host or port. Port mirroring is most often used in conjunction with a packet analyzer, also known as a packet sniffer or network sniffer. Administrators often use port mirroring to examine the flow of traffic to determine what method of network optimization to use, or for when they're determining which security measures to put in place. Port mirroring can create a significant amount of network overhead, so it should be used sparingly on an active network, and you may want to shut it down once your research has concluded. That concludes this session on configuring switches part 2. I talked about installation considerations, and then I talked about configuring the switch port itself. On behalf of PACE IT, thank you for watching this session, and I look forward to doing another one. Hello, I'm Brian Farrell, and welcome to PACE IT's session on wireless LAN infrastructure Part 1. Today I'm going to give an introduction to wireless network standards, then I'm going to move on to antenna technology, and we will conclude with wireless access points. There is a whole plethora of information to impart, not a lot of time, so let's go ahead and begin this session. I'm going to begin by giving an introduction to wireless network standards. To talk about the standards, I need to introduce you to the IEEE 802.11 specifications. These are a set of specifications that deal with the data link layer and the physical layer of the OSI reference model. These establish how wireless network communication can occur. The 802.11 standard specifies the use of unlicensed radio frequency bands as the carrier for network traffic. It also specifies that network communication will be half duplex in nature. and that it will be implemented using carrier sense multiple access with collision avoidance, or CSMA-CA. Carrier sense multiple access with collision avoidance technology requires that devices only transmit data when no other data transmission signal is present on the carrier wave. Now, the 802.11 standards have been amended over time to become our common standards that we see today. These standards include the 802.11b wireless standard. It was commercially released in 1997 and operates within the 2.4 gigahertz industrial, scientific, and medical, or ISM, radio frequency band. Now, within the 2.4 gigahertz RF band, it uses multiple channels that are 22 megahertz wide. There are 11 separate channels, of which only 3 do not overlap. 802.11b has a theoretical throughput of 11 megabits per second, and it is compatible with the 802.11g and N standards. Then there's 802.11a. It was also commercially released in 1997 and operates within the 5 gigahertz unlicensed National Information Infrastructure, or U-NII, radio frequency band. It offers up to 23 separate channels that offer a bandwidth of 20 megahertz each. None of the channels overlap. 802.11a has a theoretical throughput of 54 megabits per second. It is not compatible with any other standard. 802.11g was commercially released in 2003 and operates within the 2.4 gigahertz radio frequency band, just like 802.11b. It also offers a bandwidth of 20 megahertz on 11 separate channels. It has a theoretical throughput of 54 megabits per second, and it's also compatible with 802.11b. It's also compatible with 802.11n and 802.11ac. And that brings us to 802.11n. It was commercially released in 2009 and can operate on both the 2.4 gigahertz and 5 gigahertz radio frequency bands at the same time. It uses a 20 megahertz wide channel within the 2.4 gigahertz band and a 40 megahertz wide channel within the 5 gigahertz band. It has a theoretical throughput of 600 megabits per second through the introduction of multiple input and multiple output MIMO technology and beamforming. And it is compatible with .11b, .11g, and .11ac. And that brings us to 802.11ac. It was commercially released in 2013 and operates on the 5 gigahertz radio frequency band. The available bandwidth varies by administrative settings and can be dynamically changed by the wireless access point based on how much radio frequency interference, or RFI, is present and how many users are on the wireless network. 802.11ac has a theoretical throughput of over 1 gigabit per second through the introduction of multi-user, multiple input and multiple output technology, or MU-MIMO technology, and beamforming. 802.11ac is only compatible with 802.11g and N. So why broadcast a wide signal to a specific device when it's possible to target that device specifically? This is the question that beamforming answered. Once a device makes a connection to an access point that is capable of beamforming, the AP will auto-tune its antenna and transmitter to more specifically target the device when communication occurs. This can reduce RFI and increase throughput on the wireless local area network. While 802.11n allowed for beamforming, it was not a standardized option until the implementation of 802.11ac. Since we've covered the standards, let's move on to antenna technology. First up, the basics. Antennas are used to broadcast and receive radio frequency signals, and they fall into two basic categories. There are omnidirectional antennas, which are designed to broadcast and receive signals in all directions. Then there are unidirectional antennas, which are designed to broadcast and receive signals in a specific direction. Antenna placement and type of antenna will have an impact on wireless local area network performance. Both MIMO and MU-MIMO are technologies that allow for more than one spatial stream to be transmitted and received by a single device through the use of multiple antennas. MIMO allows for up to 4 spatial channels, while MU-MIMO allows for up to 8 spatial channels. MU-MIMO also allows for a single signal to be spread across multiple transmitters. This accounts for the multiple user part of the name. Let's conclude with a discussion on wireless access points. The wireless access point is a foundational piece of the wireless local area network. The wireless access point, or WAP, can also be known as an access point, or AP, and it creates a point of entry for wireless to enter the more traditional wired networking environment. The AP can also be used to join other types of networks. Wireless access points in most cases use unlicensed radio frequency bands in order to communicate with devices. One or more antennas are used in order to radiate and receive radio frequency signals in a half-duplex manner. Wireless routers are common in the small office, home office environment. They are wireless access points that have routers built